Right, welcome everybody, how we're doing. So, camera. Oh, fine. That'll do. Right, headphones. Right, so, welcome. Last stream, we kind of done a bit of a reboot on the cluster LOD sort of stuff. So we just sort of rewrote the plan out with a slight new design. And we're sort of sketching out the volume constructor shader. I'm thinking we can still make it just a single shader, whereas in the previous one we've done, there was like 5 shaders or something like that. So I'm just gonna, I've worked a little bit on it off stream, so I'm just gonna go over those little changes now, and then we're gonna get into finishing off this sort of pseudocode for this compute shader, and I'll just sort of explain it from the beginning with some drawings, and we'll continue on and finish it today, and maybe even get started on it. So, right, I said that I could probably get rid of the 256 cubed limit completely and have it like an infinite volume that you can sort of fill in. A bit like how this drawing application allows you to infinitely draw on some infinitely big canvas. But I was thinking about how I might do that. And there are some complications that I think for a first version, we might as well just avoid those. So 256 limit, I didn't like this one. We downsized it because I couldn't do the 1024 one. But happy news is I can do the 1024 one with this new design. So the thing we've got to be careful about is 1024 cubed is 1 giga. 1024 cubed is 1 gigaspheres. So we just got to be careful. Like we don't want to be using 1 gig or more of RAM. Just for spheres, so we've got to simplify stuff that's not on the edge of a model, right? So stuff like in here would just get simplified to bigger spheres, and the ones around the edge would be smaller. Yeah. So 1024 means you could have spheres that are about 1 mil in size for a meter wide model, right? And if you want 2 meters, you do 2 mil, right? So it's a good good size, I reckon. So that's something. So we've got the restriction back. It keeps things simpler. When we was doing this sort of bone thing, we came up with a bunch of different ways of doing the bone, how we store the bones, and the weights. And it was using a lot of memory if we did it per sphere. So we found different alternatives, but I thought of another one off stream and I put it in. So I'll just go over this one. So the idea is like we've got a cluster which is 4x4 now. This is our new cluster size rather than 2x2. I don't know why I got that. Oh. Right, okay. We're gonna have to draw another one of these unless I can get the eraser and yes, just get rid of this one and start again. So because that's not a good one anymore. So basically we've got a 4x4x4. The perfect circles. One more. These are not so good. Right, so we've got a cluster which is a 4x4x4 of spheres. So obviously this is a 2D slice, but you get the idea. So the basic idea, right, is if you used to store a bone and a weight, so a bone would be 2 bytes, and a weight is kind of like you want 1 byte, and it's a normalized number between 0 to 1. Um, if you store that per sphere and you have like tons of spheres, it adds up quickly. So I was thinking about adding it per cluster, and you put the weights on the corners. Um, so you put your bones. So you have a unique set of 8 bones per cluster, and you have a unique set of weights per corner. So the beauty of this is, right, you got 8 corners. So the weights go here, right? And everything in between is just a trilinear interpolation. So if you want like the weight, what is the weight for this one? Well, it's just a trilinear interpolation from over the x-axis. Wait, it's not even corners. Is it corners? Uh, yeah, it's the corner. It's not a trilinear interpolation then, is it? Because you what if you got a different one? It might be a trilip. Yeah, something like that. And then you also obviously cross the z-axis as well. So you'll just interpolate the weights for each of the bones. Bones there. Yeah, got myself a haircut. Give myself a nice shave. Got to finish up on some touch-ups though, because um, I lost my template, so I can't do it quick anymore. I've literally got to sculpt my face manually. But yeah, just wanna not look like well, it's really warm over there, so you could get the haircut. That'd be good for a month. And I come back with long hair again. Locally. Locally all the way. Um, I use the cloud for backup, right? Yeah, so I got the code repos backed up on someone else's computer, or, on a server, like GitLab or whatever. So if anything happens with my local copy, it's backed up on the cloud or whatever you want to call it, right? But local all the way, because then you have access to it, right? Local first. That's what you want. How about you, Gabby? How's it going, Cat Payne? How you been? Hope you're doing well. What else did I add to this plan? Yes, we're doing 4x4x4 now, 4 cubed clusters. We're not doing 8s. Oh yeah, that's the other thing. We was planning on doing an octree still, even though we had 4x4 clusters. Turns out, terrible idea, and we'll go into it very briefly. If we only divided like an octree, right, to get 8 nodes, you're basically doubling it across each axis every time instead of so if you try and work out like so say if you want to fill up a 1024 volume, you still need 500 and what is that, right? I think you still need 512. Yeah, no, because on L0, LOD 0, you just have one cluster. LOD 1, you'll have 2 clusters, right? Of 4. So you just have 8, so you've just doubled it, right? And then you have 12. Let's divide by... Yeah, so yeah, you'll need more LODs, basically. So it'll basically be 4 times 2. Damn it. Yeah, it'll be 4 times 2 times 2 times 2. So that'll be LOD 4 is 32. So you're doing 4, 8, 16, 32. Whereas if you did it, we're going to do it where each sphere gets its own child cluster of 4x4x4. So that'd be 4, 16, 64, 128 or whatever. Sorry. Wait, sorry. I forget. And also bad at maths. 256, that one. Yeah, so instead of being at 32 spheres, wide at level 3, that would have been LOD 3. You would be at 256. So you need less levels of detail if you do it this way, and it's not a big deal. I was thinking there was a bit of a problem where I was thinking the beautiful thing about it as an octree, you can get a 2x2 and then like downsample that nicely in the parent cluster. But I've decided that it probably doesn't matter. We can probably do a downsample with all of the things in a cluster that go down to one sphere, maybe. It should be alright. Because you'll get all... It'll be alright. So that's the other change I made since last stream offline. And then I also improved the plan a little bit more. So we're just going to go over the plan from the beginning. This is hopefully the single shader. And we can just construct this tree of spheres. And the aim is what's trying to avoid allocating too much memory, right? We've got a 1024 cubed space that we can build in, which is 1 gigaspheres, right? So if your sphere takes up like, if your sphere takes up, say it takes up 2 bytes of memory, that's 2 gig, right? So we have to simplify where possible and avoid creating excess clusters where we don't need them, that sort of thing. So so this algorithm is gonna solve that, basically. So we have larger spheres where they're surrounded by, spheres from all the way around, right? So I should have my box around my cluster. Each cluster needs a box. This is going to be amazing. Yeah, rest in peace, Beard. Life is going seemingly well. Awesome, good to hear that campaign. Hey there, Sully. How you doing? So, the volume constructor. It's basically there's a queue. Now, let me think about this. So the idea is we still want to process 256 cubed. Like to stop going over to the to-do plan here. Save some memory. So we know if we focus on, the first 256 cubed area, that's only 16 megabytes it's only 16 mega, multiplied by whatever, right? Megabytes. Area, meaning that's a piece of cake to store in RAM. So if we process 256 cubed areas at a time, so we need to process 8 separate places of a 1024 cubed volume. We could sweep through this thing over so many frames that we budget for. We could budget, say, for 100,000 clusters can be processed in one frame, for instance. Maybe there's that budget, and we pause it. And we also only process each sort of quadrant, 256 cubed area at a time until we process the next area. And that will mean that we can stay within this budget because we can process the whole thing and simplify it. I think. Is that right? Well, you have the problem with the... No, it's possible. Yeah. Just the edges. Yeah, it is possible. You might have a few clusters left over, though. So, I was going to have an idea of 2 separate ring buffers. where you have one which has higher priority. But thinking about it, we might need two ring buffers. One is just going to be hold the node to the next. Um, you might need like an array of 8. So you'll go down to the first LOD. On L0 might be special, and that might be in a separate shader then, where you basically just, or maybe, yeah, so you have the volume constructor initializer shader, and this one is just going to literally like, allocate, you basically want to allocate, hmm, hmm. So you've got L0, which is the first sort of like cluster, and it has like 64 children, right? 4 times 4 times 4. Um, Wait a minute. That's already wrong, isn't it? I was thinking, hmm, maybe we build it into the shader. Maybe we just have an if statement to say, hey, if this cluster's kind of in the wrong, how do we know if we've finished it though? That's the thing. How do we know if we've finished the cluster? Hey, the campaign. I've been doing a simple radar project, just spheres moving around on the screen to check for collisions. Awesome. I've encountered the tunneling problem, and I need to implement a quad tree implementation. It's a pretty good learning curve so far. I've just for information, I suppose. Awesome. Yeah, I think with the what you're saying there with the tunneling, that's not necessarily solved by the quad tree, right? So the quad tree, from my understanding, I'm not a physics expert, but basically you've got two problems in. Well, you got a problem in physics, right? You don't. You've got like n, which that equals the number of objects, right? And you need to like, you don't want to have an n times n, right? Or an n squared, right? Complexity when you test all your objects with each other, right? Because at the end of the day, that's the computation you need to do. So to make it not this, you need what's known as there's an arrow phase, which does the sphere versus sphere collision detection, right? Where they have boxing gloves and they punch it up, and then you have the octree or quadtree, where it's basically saying, hey, these spheres are in here, and these two can test against each other, but you don't have to test against these boys, right? Only these have to test against these against these. But yeah. So it's just a way to stop it becoming like an n squared. Yeah. But yeah, the tunneling problem, that's a different problem entirely. You need to either switch to um, sweep based collision detection, or you need to have big enough objects and fast enough tick rate, basically. So it's not a problem. Yeah, those are your options. Yeah, physics is cool. I want to explore that some more, but it's one of those time things. Yeah, one day. Maybe we do like a fighting game or something. I'll do my own physics because it's quite custom. I'll probably do my own physics anyway because it's something that's cool to do. So how are we gonna solve like the problem of like waiting for a certain area to be done? So you could put an if statement around the cluster you've taken. Yeah, okay, that's the question. It's like, how do you solve the? How do you know that you've completely finished doing that sort of area? So they tunnel. Hmm, yeah, awesome. That's so weird. What do you mean? You might hit that problem there. Oh, right, with the the phasing. Yeah, probably, probably. So you got the cluster, and you realize it's in the wrong. Like it's not one that we're processing yet, or something like this. Um, yes. Yeah, so how do we know? So we've got this like 1024. Right. Okay, we're gonna add more crossing out here because I can't. All right. Get the eraser. There we go. So we're going back to 1024. Oh yeah, 1024. So the problem we're trying to deal with is uh is the following, right? We want to break it into like only process 256 the 256 area at a time. Because then we know, hey, this fits into 16 megs of memory, all good. So it's not too bad to build something in there temporarily, simplify it, and you've got like less than 16 gigs of memory used, and you can do that for the whole, for 16 megabytes of memory. That's what I meant. Yeah, 16 megs of memory. That's easy to store on GPU, and then you can simplify it. They need to come up with a way when we process um, the edits and form the spheres in here. How do we say like? Because the problem is the clusters, they will have 64 children, right? 4 by 4 by 4. And their children will come and mark a bit to say, hey, I've simplified all of my children, so now you can simplify yourself, right? Um, but so ideally you could say, okay, well, when when like basically like the cluster that, how many clusters will it be though? Because it's not evenly spread because it's 4 by 4 by 4. You'll get two clusters. Sorry, you'll get 8 clusters, right? You'll get 8 clusters on L1, LOD1, which are in this area. Um, so you could pre-allocate L. Anyway, yeah, I think we just got to do the 2Q method. Well, we'll have a so we'll have an initial shader which sort of like kicks off the initial so the initializer which will kick off L1 basically. So allocate L0 and L1 nodes, cluster nodes, right? Clusters. And then you want to store you want to store you want to then sort of place, you know, you then place them onto a ring. Yeah, you place L0, or you place 8 L1 nodes on the process queue. Could it be a random mate, or does it have to be? Yeah, we're better off with the ones in the same area, right? That lay in the same sort of 256 cubed area on the process queue, and then you'll place the rest, the L0, or the rest of the L1. Let's call them clusters onto a sort of this is a sort of standby queue, I don't know, and the L0 node, L0 cluster, okay, onto the standby queue. So this means that when we completely run out of nodes to process, we pull 8 off of the standby queue or something like that, and place them on. Yeah, but the L's, okay. Well, don't put the L0 on there. So basically, we'll have one queue now. We'll have the process queue, as we call them, with the standby queue. 2 queues, but one process queue. We take off the process queue. Then we want to say if all of our worker threads, if all worker threads are waiting, right? If all worker threads are waiting, then take move sort of 8 nodes, 8 clusters from the standby queue into the process queue. Something like that. And then we want to say if the standby queue is empty, standby queue has clusters. Else, what are we going to do if so if the standby queue then doesn't have anything, then we process the final L0 node and sort of terminate worker threads, right? Interesting. So this is like essentially a little like job queue where we're just taking a job off. Each thread group gets the same job, and there's 64 threads processing each sphere or child of that. Each sphere or child of that cluster, right? So 4x4 set of spheres and children nodes. So essentially it's like a ring buffer of jobs, basically. And the job would be to either tunnel down yeah, okay, this is something we've got to think about. So the idea, right, is what these clusters that we're going to be creating from a list of like edit operations, and for now we're just going to have cuboids and ellipsoids, and you can sort of fill this 1024 cubed area with these things, and they'll get filled in with spheres basically, right? So basically, um, um, these list of edits, right? As we go down this sort of area, they only apply like when you sort of brush this thing over this area. These nodes over here that are getting processed don't need to process this element. So we make a little list. As we go down the tree, we rewrite or we make a new little array for all the child nodes. Basically. And we get rid of ones that don't need to be there so that it's just quicker to process as you go down the tree. So you pick up a node and it's either in being told to tunnel down, or if it isn't being told to tunnel down, it's going to tunnel up. When you tunnel down, if nothing happens, you will tunnel up. And when you go up, you basically simplify. But we try to avoid tunneling down where possible. So the idea is you can paint at different LODs explicitly. This is how you have different sizing. So you can actually have different sized balls as an art style, as a sort of to help with the thing you're artistically creating, right? You don't have everything be the same size. So you can create these sort of bigger spheres at the higher LOD. They're still on the grid, but on the higher LOD grid. So if you're at that target LOD, if your cluster's at the LOD of the edit, then you just basically create the spheres there, right? It's just a bit set of, it's just 64, it's two 32-bit integers, and you just basically set that up. Whereas if it's greater, then you append this edit to the array of indices that affect the child node, right? So say if you have each of these spheres have a children which they point to potentially, right? So if you have an edit which sort of goes like that, it doesn't affect these guys here, so we don't bother putting it in the arrays we make for those guys. So there's that. So arrays are just a linked list of chunks. They're going to be 16 edit indices, so they're 64 bytes a chunk. So hopefully it's just nice cache wise. And you're processing like a linked list of elements. You put in one cache line and process that, and then link to the next one if there is any more. And this way it solves the problem of growing multiple arrays at the same time, which we don't know the final size of. So there'll be a tiny bit of wastage up to 15 elements at most, or maybe 14 actually, because we need one index for the next link. And if this edit fully covers a child node, then we can mark this child node as being refined already, so you don't need to go and tunnel down. So the idea is if you've done some edits like, I'm painting over this sort of area, but it's in the higher level of detail, which we'll link to, right? These children will link to, and this edit will have to go through to those guys. Well, what happens is after this, you have a massive sphere that deletes this area, right? Well, you don't need to go down there anymore, because the final thing that came on actually just deleted. I just deleted it, right? So we can basically mark this as being fully refined already, and we don't have to bother going down. We can just paint the spheres in there, and jobs are good. Wait. What can we do? That's not fully true. So the thing we need to make sure is gotta be careful here. So we want to make sure that it's at least covering the ones to the left and the ones to the right. You know, so if it's like, if the sphere or the box, or the ellipse or the box, whatever it is, right, is bigger than sort of that. Yeah, so it at least has a cluster either side of it. We don't bother having to process this guy any further, right? And it is the last one. So you have to say, like, if the edit fully cover... so two things, right? The deletion is 100% correct. Where if it ends on a delete, then, like, so you want to say, if this edit is a delete and fully covers the chart, then mark this node as refined, and then we'll go down. Right, and then you want to do an else if this edit is an add, and you fully and it covers It's a thing where you want like a signed distance, basically. You want to get a signed distance and know, hey, I'm this much distance from the edge, and you've got to be a cluster big, you know, more than a cluster and a half away, or whatever it is, right? And its signed distance is negative cluster and a half. Right. Is less than cluster and a half. Then we want to sort of mark this child as refined and place a sphere, right? Now the thing is like, as refined, but you want to say like, then mark that we need a sphere. Yeah, it's like you want to put a sphere, you want to mark that we need a sphere here if we stay refined, right? Something like that. And then basically when we, so we say like, if we are refined, if refined and need a sphere, sort of place a sphere down, right? Place a sphere down. Something like that. Yeah, so that's good. Right. So that this means we can avoid processing entire clusters of higher detail that we don't need to, so long as the edits that people do cover that area. But in cases where they don't, we have to simplify and come back up the tree, and there's just no way we can avoid that. Hence why we're only processing sub areas first, right? We're only doing 256 cubed areas at a time, but it's fine. Okay, so there's one more interesting thing I want to go over, and that is the way, the sort of the problem that it brings having different target LODs. So we can so when we have our edits that work inside this 1024 cubed area, you can say, hey, I've got a big sphere. I want to have a brush which is maybe an ellipse or whatever like that, and I'm painting at an LOD which is bigger. I'm not painting at the smallest detail. I want to paint at a bigger detail because I would like to see, it's an artistic thing, right? I would like to see bigger spheres rather than smaller spheres, right? When I paint down. So that's really cool, but it brings a problem. where, oh, what is it? So you're gonna paint down. Yeah. So what I want to do, which I didn't have in the past, is you can paint down to that LOD, sure. But the beautiful thing is you can also paint in the same, because everything is gridded, right? You can paint inside the same grid area and put smaller spheres, and it won't delete it. In the previous version we've written, it would delete it. But I want to keep it there because it could be some artistic thing, right? You might want to have a sphere surrounded by smaller spheres or whatever. Maybe they look like they're supporting it or something. I don't know. But so because we're having that flexibility, we no longer have a lower. Wait, do we? Is it because of that? This is so complicated. It's hard to forget. It's hard to remember sometimes. These things. So if you have those lower LOD, higher LOD spheres, the smaller ones, they are going to, and you simplify, I guess. You don't, like, you've already painted one of those guys down. And I guess these smaller ones, they don't contribute to that lower LOD sphere anymore. I don't know. Oh, this is something maybe. You could say if you've got a higher LOD sphere there, higher LOD sphere, and you brush. Yeah. Yeah, I was thinking maybe that if you did a high LOD sphere inside of one of these, you could probably optimize and not do that. But I think we'll leave that optimization because it's a little bit more tricky. I think there's an issue with like deleting now, where if you delete, I think I'll just delete everything that's in its. Yeah, that's fine. We'll just delete everything that's in its place. That's right. Yeah, we won't worry about those optimizations. We can do that later if need be. But there's another issue then. Now, here's something that I see a problem, right? You might build a house, right? And you've built like a, we're saying it, right? It's a bit 3D here. So you build like a little house, right? And the beautiful thing is with this house is, you know, it's okay. Why did I say beautiful? The ugly thing about this house is that when you zoom out, so you've built it up with loads of little spheres. When you zoom out, randomly the walls just disappear. You're like, why does this disappear? Well, because what happened is you built thin, like, kind of thin walls, and the way the LOD thing will work is basically if you've got 90%, I think, with going with, of your 4x4x4, will it place a single sphere down in the lower level of detail, right? all of these will downsample into something like that in a low level detail, right? So you could think as you go up your LODs, this thing could disappear earlier. So what we want to achieve is a way to paint down a sort of lower level, like you just imagine you have like massive walls on the inside where you don't really care. When you're far enough away, you just have these bigger spheres in there, and they will still stay. The walls will still stay from like this big, maybe, I don't know, and they won't disappear early. Maybe. So it's like an artistic thing. Like when you build the model, you can control that by painting explicitly. This is only when it's this is only to be displayed when we're at this LOD, right? So it's like so when you paint down, this is where I'm going to think maybe we have to have two different bit sets. So when you do your cluster selection, when you are selecting a cluster, an LOD to render, you're going to have some of your previous clusters get rendered because they've got this sort of edits that you've applied, and you're painting down here because you want these to be visible. You just want larger spheres to be visible in general, even when you're sort of viewing the micro detail. You've got these larger spheres for the artistic style, right? But you also want to have other spheres where you go, no, hang on a minute, we're viewing this cluster at this LOD, and it would be nicer if we had these larger spheres because it represents the thing better when it from a zoomed out perspective or something like that, right? And that's nice to have that control. So I think what we need is to have a sort of an explicit LOD layer where it overwrites the the other one. So we might double the memory, basically, the sphere memory. Carrot juice. No, this is Fanta fruit twist. Isn't the sphere packing problem unsolvable? What do you mean by packing? Do you mean like I'm not sure what you mean by that exactly. Can you go rephrase that, please? Hey Chandu, how's it going? Welcome back. Clusters, are you doing some kind of distributed system stuff? No. No. So clusters in this terminology simply just means a cluster of 4x4x4 spheres. So you can basically occlusion coal or you can occlusion coal 64 spheres at a time, or more basically. It's a tree of clusters, so you can occlude their parent and all the child ancestors at the same time. So we're thinking about having another layer, spheres, and having two layers. So a cluster is a node of 4x4 children, clusters, and spheres, as well as an extra layer of explicit LOD spheres for controlling how the model looks zoomed out, right? So you need the explicit layer, right? So these spheres only render when wait a minute, when do they render? Because say if you select LOD3, yeah. These only render when cluster selection stops at LODX and cluster is LODX. Something like that. Probably a good fine way of saying it. So like if you have a volume, There's many ways to fill that volume with same-sized spheres. You can't find out one that's the most optimal greatest number of spheres. That's the greatest number of spheres. So I'm not sure the question exactly, but let me just go over how the system works. So you have those edits, which basically you record the history of how you sort of build the thing. So you say, hey, I've got this, let's do boxes. I've got a box brush, and I go over and then these things get sort of filled with spheres by this compute shader, right? So basically we're going down in clusters of, so LOD 1 will look like this but in 3D, right? And I'm only processing each 256 region at a time, which means the amount of memory I can have in my builder, in my sort of volume constructor thing, I probably need about 16 megs times by size of clusters and spheres or whatever. So it means I can build in this space, go all the way down to the highest detail that the edits have in this space, simplify the crap out of it where possible. So say if this whole area is filled with spheres, well, these spheres here can be simplified to be bigger spheres because they're not on the surface, and the smaller spheres can be around the edges, right? You will see this if we have animation and it breaks apart, but that's fine because it's part of the style that we're having. So that's how we solve. I think that answers your question. I'm not quite sure what the question was though. Fully. Another random question: do you work on networking stuff? No, I just do graphics and that engine work professionally. But I've looked into networking and that. It seems interesting. It's one of those things I do definitely want to try because it seems like fun. Just not got really the time or around to doing it yet. But maybe for this game we might do it. But it's one of those things where it would add extra work that might not be necessary. But it could be necessary, right? Depending on the game. Yeah. Where's my music gone? Right. So the explicit LOD thing is great because it means that we can control, like, hey, when this thing zooms out, it doesn't disappear. And that's cool. So we'll need that on the edit, on the volume paint, on the material cluster tree. We would also need a layer of would need an explicit. Yeah, we need an extra bit set for the explicit ones as well, or extra red materials for those too. That's fine. That'll be alright. Okay, so we solved that problem now. Big fan of that. So we can now. Right, is there anything else about this? Okay, so we've solved the problem where we tunnel down. Now there is some optimizations we could make in the future, but for now this is good enough. Maybe we can skip this optimization initially when we just build it, because it's just nice to get things up and running quicker, isn't it? If a child node is unrefined and has edits, append each child node to the, it's not the tunnel down queue anymore, it's the process queue. Else, if refined, I need a sphere, place sphere down, tunnel up equal true. So now you're in the tunnel up mode if you reach here, because we didn't actually put any children down, so we are the leaf, and we tunnel up. So tunnel up is about taking each child node Is that right? You're not child node. Each sphere and take each sphere. All right. If we have 0.9%, wait, 90%, let's just say it that way then. If we have 90% spheres or more, let's just say plus, then place a sphere for it in the parent cluster, and we want to mark the parent cluster, mark that we have visited the parent cluster, or we have mark that we have yeah, we have visited the parent cluster, something like that. If we're the last child to visit the parent cluster, then not traverse up, then place the parent cluster on the process queue, which another worker thread will pick up. So then this will finish here and we'll say continue to get the next job. That's right, isn't it? Excellent. So I think this is the plan. Not gonna lie. So I think we can actually... No, there's one thing that we're missing. I just realized now. One more thing. We have to make the simplify better, because what we don't do... so this just makes the lower LOD spheres. We probably want to say if it doesn't have one or something like that, but yeah, this just makes the lower LOD spheres. It doesn't get rid of the children that are no longer needed. So when is a child no longer needed? When, say if you have this area that's filled with spheres, right? You want bigger spheres, even if we painted in ultra high detail, tiny spheres here. You know, they're completely surrounded by other spheres, so the detail's not needed there. Right, that's the beauty of triangle meshes, is the detail is only on the surface, right? So we need to try and be comparable with that, so the way we do it is with the bigger spheres. So how do we achieve that? Well, currently, and in the current version which we built, we have this thing called an occupation map. So we're going to bring back the occupation map, and it's fine, I think. Yeah, so with the occupation map, right? Right. Let me write down something I've just forgotten about. Don't want to forget this. So you've sort of when you place down on parent, when you place parent cluster in process queue, what happens if we are LOD 1? Maybe that's not a problem, but I want to just 0/1. Okay. Right, back to the other train of thought. So we've got the occupation map. So this thing is really great. And we've already done the thinking for this. So all the code's already been written out for it, which is great. Where is it? Occupation map. Yeah, so basically it's just a 3D bit set. It's a 3D texture where you got a bit set, and it's I'm forgetting the details on this. But the beautiful thing is we get to quickly check with 2 samples if a cluster is surrounded by other clusters in 3D, which is great. So we have to fill it up because it needs a downsample pass. I'm glad I looked at the code now, I would have forgotten about it. So I don't want to break it into separate passes. We've been able to build the whole thing in like a... Yeah, so the way this occupation map works, each bit in the bit set is... Where's the thing? Here it is. Right, each bit in the bit set represents a cluster. So you've got, in your 3D texture, you've got a 4 by 4 by 2, right, for 32 bits. And basically, we only write to these 2 by 2 by 2, and all of these are repeats from the clusters that come to the right, diagonal, down. And this means that we can then sample in the future if we have repeated information. So you can think of where we actually have like technically a 2 by 2 by 2, where the extra information is just repeated from the other ones, right? The neighboring 2 by 2 by 2s. And the beautiful thing about this is we can then look for our cluster. So we then sample from it, our cluster that we look for has to reside in this area. And if it doesn't, if it resides in this area, you just look at in the next one to the right in that area, right? It's very easy to work out. But it means that if our cluster that we're checking that if it's surrounded by other clusters, it has to be in this area, because if it's here, we literally just have to look at the bits around here, and we don't have to check any other bit sets at all. So you can do it in 2 samples. You can sample 2 layers of 32-bit integers, and that gets you a 4 by 4 by 4, and you can just check the neighbors very easy, very quickly. So I'm thinking about building this thing considering we're only doing a 256 cubed area at a time, which means we could probably get away with so I don't want to do the 1024 cubes because that's a 1 giga or whatever. You know, we divide by, it would be, what do we divide by, wait, what would it be? Sorry, it'd be 1024 divided by 8, no, 512, wait a minute, 1024 is the number of spheres. You got 4 by 4 clusters. So a cluster is actually, so if you just divide it by 4, which is 256, right? So maybe this is feasible, just have a full-on big one in memory. It might be all right. So because it's 256, you need a bit for each of those. So that's just divide by, where this is across one axis, so you've got to be careful. You got 2 by 2 by 2. So if you divide by, oh crap, it's 128, right? Divide by 2. Yes. And then, so there's that cubed, which is 2 megabytes of memory. Maybe it's fine. 2 megabytes of memory. And then, what else? It might be times by 4 because you need, yes, 2 mega words, and then the word size is 4. Is that right? 3 times by 4. What the crap's going on with this thing? Did I press the wrong thing? There we go. 8 megabytes for this thing, which is that's like no memory. So that should be alright. So we can actually have a full-on one of these that we need a full MIP chain as well, so add half or something like that. Wait, that was only across one dimension. Crap. No. I cubed it. Right, that's fine. So, you've got that bit set now. The problem is the downsampling now. So the issue is we used to run multiple passes where after we generate the initial tree, we used to run this generate occupation map, which was great, it was fine. But we did it for the highest level of detail. We just filled in all the clusters in 256 cube space, but instead anyway, 256 cubed amount of spheres. We'd fill it in. Then we would downsample to get full MIP chain, full pyramid, right? So it's a custom downsample because there's repeated information in this thing. And then when we try to do the refine afterwards, it's a lovely couple of samples, do some bit tricks to sort of shift it around into the right place. Then it's just a simple two, checks to make sure the bits are the same. And if they are, a cluster is fully surrounded by other clusters. It's very nice and simple, quick as well. But in this new design, we kind of just designed something in a single pass, which is really great, but for the simplification, it's not gonna work. So maybe what we could do is design it where like we need the simplifier to happen. So is there a way where we could build a downsampled version of this cluster is full? I don't think there is. While we're building this tree. Because it's about knowing if a cluster is full, and you only know when you go up the tree and do like lower LODs and things. Wait a minute. You know a cluster is full when you've processed the highest level of detail and stuff simplifies. Down to, a low level of detail. That's anything time when you know, isn't it? So we might have to break it into two passes. Hmm. Yeah, maybe we need to keep the pass system where so you process one area. Or we just go back to the 256 cubed areas again. Yeah, maybe we just go back to 256 cubed areas because then we don't have to worry about. But the problem is the refinement will sort of be broken into a separate stage. Yeah, so we might extend the. All right, here's what we might do. First version, we might go back to the 256 area again, and then in a future version, we'll extend it to 1024. So we just get more space to play around in and build like higher fidelity models, basically. But yeah, I think that'll be That'd be good, just to get something up and running. Um, why 256, by the way? Do you not have a cluster with that? So the thing is about the 256 cubed is it's a great, like, we don't I need to pre-allocate some memory, like, so rather than build a complex sort of tree structure on the GPU and use like the same allocator that all the built volumes have used, and then realize that when I'm sort of halfway through building this this volume, I realize that crap, I've run out of memory. Like, you can kind of tell up front how much memory you needed. So to fix that problem, I'm pre-allocating a region of memory where this is the maximum space to build the volume constructor will use. So we just pre-allocate it. This way, when we sub-allocate from this, like, we know it's going to build in here okay, and we can complete it. And then we can look at it and be like, hang on a minute, this doesn't quite fit into memory. So we will, this doesn't quite fit into our memory. So we just simply won't put it in there and do something else. So that's the reason why 256 is good, because 256 cubed is 16 meg. So you got plenty of, that's a drop in the water of memory. If you times it by 4, times it by even by 16, it's probably not so bad, right? It's only 256 megabytes, right? Compared to 1024 cubed area, that you get is the gigabytes. So it's not the best to work with, but I was thinking I could build it if I build it in 256 increments. But yeah, there's no good way other than doing it 256 increments. So right, switch to that water. So we switch to 256 cubed area again. We'll definitely be able to get up and running quicker. It's basically the same system. I think the system is very close, but we just have 4 cubed areas instead, and we're doing a different way of building it. The problem is, though, so if you do this, where you construct it, you still have to run the occupation map generation stage downsampler after that, and then you have to run a shader afterwards, which does the refinement. Now, we can go down from the top of the tree again, and we can say, go down from the top of the tree, and you check the occupation map and see if it's surrounded, and if it is, you get rid of it and all of its children. Yes. Which might be a bit of a, yeah, you'd need to sort of, yeah, we can make that multi-threaded. Okay, I think we could do the 1024 version. It might be possible. You'd have to just remember, you have to keep a separate queue around. Um, so you processed all the clusters. So we won't need that if it to continuously continue anymore. Right. Yeah, I think we can just yeah, we can do the 1024 then. Area. So what is this thing that I remember? So place the parent when you place the parent cluster onto the process queue, what happens if it's L1 or L0? So you're tunneling up. You only tunnel up if all of the children are that, right? Yeah, that's never a problem. Because you have to wait for all of the children to get there, which they wouldn't be until you start it off. Excellent. Okay, I think we've got it all sussed out now. So effectively, this is the first shader we've got to rewrite. But we get to keep a lot of the complicated code that we've already written out, which is really good. So this shader gets rewritten where we construct the initial leaf spheres. We need to, but we're going to keep this occupation map generation downsampler. The refine LOD is going to be kept as well, but the way they kick stuff off is going to be different. So we're going to go into the data structures and rework that. Before I do that though, I want to take some timings and see sort of like how fast this one is, and then just yeah, so it's taking about 3 milliseconds to build this area, which is way too much. We've only put one edit down. It's terrible. I think it's just the way we chain through the tree. I'm not sure, but it might yeah. So I'm gonna take a screenshot of that and put it on the Discord, and then so we've got a little backup, so we can sort of compare it. So we're just gonna say like, you know, a after the rewrite. There we go. Okay. So let's make our way on it. So let's redesign the data structures first. I think so we're going into so let's go to the volume. So it was really cool what we came up with, but it's got to go, this unfortunately, because this doesn't make any sense anymore. We used to have this thing called a midpoint cursor where we had all of our leaf nodes on the left-hand side and all of our non-leaf nodes on the right-hand side. Now, why is this thing going? So we used to keep around a list of all the, we wanted a contiguous array of all the leaf nodes. So this is the midpoint cursor, leaf nodes on the left, the non-leaf nodes on the right. You have more leaf nodes. And the reason why we had this is because I thought it would be a good idea to start from all of the leaf nodes and then traverse up the tree because it's in a multi-threaded manner, right? It turns out when you have like hundreds of thousands of these guys, and that was another problem. We had hundreds of thousands of them because we were doing 2x2x2s, but now we're doing 4x4x4, so we should have less. But still, we're going to have loads. And we are going to have hundreds of thousands still, because we're going to have multiple instances and all of this. But the problem is with that is you're processing a lot of nodes, and then you're going to say, hey, these nodes are not the right LOD, so you'll go up to the parent and then you'll check those, right? And you'll keep going until you hit an LOD which is right. So that's the way I was done it initially, but turns out the better method is to actually just go down from the root, check to see if it is occlusion called, right? So you see, hey, is this thing occluded by some other thing on the screen? If it is, don't bother going down the tree anymore, right? You've just saved yourself all of that work. But obviously in reality it probably gets a bit down the tree in some cases, but you know, you process way less information. So so we're just going to have a cluster tree where it just knows the start index and the count. It was a cool idea, but you know, not needed. Cluster tree nodes start index, cluster tree nodes count. Amazing. Right. So the root node is at 0, right? Root node, aka LOD0, is the first node. All right, easy. So we're still going to build in a temporary space, and then when we copy it out, we're going to do an optimized copy out where we'll probably copy them out so all of the children, or sorry, all of the siblings and children, right, are, sorry, I just need to say one of them. All of the siblings are neighbors. So you have 64. Wait, actually, they'll be like that anyway. That's a good point. We'll go to the next thing. Because we're having 64 children per node, it's going to be quite a lot of memory to store links. Where's our other thing? So that's the volume. Right, here's our cluster node. So the cluster node, I could just call it maybe cluster. I don't know. But anyway, cluster node is what I would, yeah, it's fine. So we need a bit set. So we need 2, right? We don't need this we don't need the visit bits. We might need a final bits, but we'll keep that in a separate array if we need it. The first the second are for the visited. The third is for the final set. But you need to store a final set somewhere else, isn't it? Yeah, but you only needed that because the visit, the traversal. We don't need that anymore. Excellent. So the problem is, right, you could store 64 children indices in here. But 64 times 4 of memory. You know, which it adds up. So rather than doing like, you know, 256 bytes of memory per node, instead we're just going to allocate, like, whenever a volume has children, they all just live next to each other in memory. I was going to do this in the previous implementation, rather than storing like the 8 indices next in the node, but that was when we only had an octree. But now we have a sort of a, yeah, it's a big tree, a 64 nary tree. Children cluster node nodes start index. So we use this guy instead. So if a node has a child, right, it allocates all of them. So we're trying to keep this as small as possible, and then you just save more memory in the long run. So you need a parent node in. Do we need a parent node index? Well, you are traversing up the tree again, but we might need that in build time. Because you're coming runtime, you come at it from top down always. So we can just get rid of that. Saves us 4 bytes. We'll have a separate array for build only information, and that's fine. There's a cluster location. This is just 32-bit integer. This is just packed. It's a lovely packed thing where we pack the offset. We're doing a 1024 volume now. So yeah, we're doing a 1024 volume now. That's another thing about this. How do you know? The CPU is going to be dispatching. The compute shaders. So you need a series of 4 to get to. Yeah, let's just start with the 256 cubed area. It's just easier. Let's not do 1024. Let's do 256 cubed again. We'll see if we want to extend it to 1024. Let's just see if we can keep that one. It's just easier to work with. Otherwise we have to do multiple things. I think it can work. Alright, so we'll keep this, right? We only need... something has changed. The number of LODs has changed. Since we're not doing 2x2x2s anymore, we're doing 4x4x4s. Meaning you've started off on a higher level of detail in a sense. So we used to only have 7 LODs, right? So okay, it's changed these constants. Cluster dim is now 4. Cluster spheres count. It's the same thing. Spheres and children. Can I just say, if we get rid of spheres and just call it children, then I think it makes you know, let's keep it. So the LOD count. So you've got 4x4x4 spheres in a cluster. You're going up to 256. So there's 1 LOD, 2, 3, 4, 5, 6. Wait a minute. Oh, I'm way too fast there. I think it's 7 in total now. 1, 2, 3, 4, 5, 6. I didn't include that one, did I? 1, 2, 3, 4, 5, 6, 7. Excellent. So that's 7 now. So you have up to from L0 to L6 inclusively. So we no longer need max number leaf nodes, max number non-leaf nodes. Instead, we just need max number of cluster nodes. So this number is 256. Wait a minute. That was wrong, I think. So we need this divided by 4, right? That's the number of clusters across each dimension cubed. So it's just this many clusters now instead, which compared to that number is just far less, right? It's hundreds of thousands. So we'll be processing less clusters when we're trying to cull, right? We're culling less nodes, but more are going to make it through because it's bigger, but it should be fine. It's 8 times, it's 8. It's a division of 8 less, right? Far better. So this is, it's a comment 64 cubed. Hey there, Ransel. How you doing? Hey there, Sleepy Mushroom. How you guys doing? Welcome, welcome. Good to see you both. You guys doing good? How you doing? The beard is gone. Max volume spheres count. Yes, it's 256 cubed. Yeah, that's a good one. That's a good guess. But for the nodes, right. I'm glad I put the comment there because I would have remembered that. So it'd be 64 to the power of 2, because that's each side of a cube. Then that's the face of a cube. Times 6, each face of a cube, times 2. That's a good one. So that's less nodes to allocate there. So that's 8 times less, I think. It's far less there. So from 196,000 to 49,000. So that's the number that we allocate in our buffer. So that's specifically just for construction time only, and then we copy it to more persistent space afterwards. Max number of full volumes. I put 64, but we could probably have more than that. But that's not really a good... Anyway, we'll replace this in the future with like a graphics setting or something, I think. Volume dim, 256. Good. Cluster dim, 64. Oosh. Right, so I'm glad we've adjusted those constants now. So let's get back into the whole thing. So material was staying the same. I'm not sure if we say procedural texture, but maybe, maybe procedural. Right? That's kind of what I want to say. So that's nice. Material palette still exists. We don't store material information on the cluster tree. Instead, we'll have a separate cluster. So we're going to actually have a different cluster node. This is going to be called like the material cluster node, which we will do later because we can just get a basic version up and running. So just to note, when we do the model, we'll have a default coat and all of that, but that's not stored in it's a separate tree that gets built, which mirrors the cluster tree. So we basically just take cluster index 64 is the same cluster, like it's the same index within the two cluster trees, basically, so we can switch between them very easily. And you can swap out between different paintings, to show say different paints of that paint over the volume. So we can have different skins by just changing the material palette, because each sphere will have a material index where it's like 4 bits of information to get into this. So each sort of volume painting can have like different palettes, but then each model can also have multiple material paintings where they could just be painted completely differently. Yeah. So that would be pretty cool. And that's the same with the bone stuff. The bone stuff is going to have its own cluster tree where it has the bone information in there as well. So the great thing about this is this information can be added later and not when you sort of construct the initial volume. And it means you can make the paint and that go across multiple volume. Well, not the paint, the bones go across multiple volumes or something like this. Hey, that guy. Dude. Yo, you need more beard. Hey, I just got rid of my beard. It's all gone. Just got back from Stockholm. Waiting for the train to the bus now. Sweet. Well, I'm glad I could be your entertainment, my friend. Did you just go to did you just go to see some friends or something? So yeah, we'll change all this stuff later. We've got a new thing. Doesn't matter for now. We just want to get the volume thing up and running again. So a sphere was a sphere. So a sphere. I think we basically just need to get rid of all of this. It doesn't make any sense. We don't need this information is not stored in there. This information was useless. It was just like 2 bits of information to tell you the offset. We don't need that. We can imply that from an index. LOD, that's stored at the cluster level anyway. Don't need that. That's stored literally in the cluster's information here. In the cluster's location information, it's stored in there. The material palette, material index per sphere, that's in a separate tree. Also generated LOD, and it exists. These can just be bit set information. So we're going to get rid of that and go ham. So no longer need a sphere array. We just need bit sets. So here's our cluster. We're making things as small as possible. So what we need is a spheres bit set, and this will tell you if it exists or not. We also need an explicit LOD spheres. So this is if you explicitly paint down an LOD. For a specific LOD. And not yeah, maybe there's a better way of saying that. Explicit is probably not. Like explicit means you've just like said outright you're painting at this LOD. But you kind of want to have a you kind of want to say, hey, I'm rendering this cluster at this LOD, so use these spheres instead. If they exist, is that a good way of saying it? Yeah, but why does it need to be a bit set? Yeah, so what needs those explicit? So you would just paint. Would it be more of like a painting thing when you paint down on the is that's not really a job of the like you would just fill in this one and say, hey, it's got spheres in there. You would just paint them in there explicitly. Oh no. It's because when you render, yeah, these ones you only render these ones if you're rendering at that cluster at that LOD exactly. If you render at a higher LOD, you ignore these spheres. That's the problem. Okay. So They better probably be called exclusive. Right, exclusive LOD spheres. That's a better way of saying it. They're exclusively for that LOD. Boom. So you need a bit set for the spheres and a bit set for the exclusive ones. Is there any other information that we need? Just 30 minutes left. There was a clarinet fest, kind of. I don't know how to explain it in English, but it's in Swedish it's called the clarinet rossa. Fair play. Festival. Gotcha. Is someone else else's fest? Maybe. Basically an event about the clarinet with lots of small concerts and masterclasses with one big concert with a clarinet choir at the end. Kind of like a festival. Awesome. Sounds like your sort of jam. Whoa, did you pick up any new tricks? Did you speak to a wise man who's been clarinetting for decades? Yeah, there's nothing else that we need to change there. That is amazing. Right. Sehr gut. Sehr gut. So we got rid of the spheres, which is great. BVH node is just standing. We're not doing BVH for a bit. There's the ellipsoid. We need to make an ellipsoid at some point. Sphere. Probably don't need sphere anymore. Model. These could really go. Don't know why they're still around. Let's get rid of them. Oh, we currently use it because we're not doing an ellipsoid yet. I don't know why. Okay. So we made the data structure changes. Now we're going to hop into the we're going to hop into the not that header file. This header file should barely even exist. Look at it, it's tiny. Anyway, back to here. So this is the internal. So this is the new stuff, and it's going to be superseded by newer stuff. So we need to figure out like what's going on here. So we don't need the children indices anymore because they're kind of part of this buffer. So this is the volume constructor stuff. The occupation stuff, map still needs to live. Very good. We don't need a spheres buffer anymore because spheres are just a bit set. We don't need the free indices buffer. That's a core allocation strategy we designed there. Don't need it anymore. Instances, cluster nodes, we need those. An edit buffer, we probably need that as we need that as well. Volumes buffer, we need that. Yeah, we just need the rest. So we can now go into the implementation file, and then we're going to go ahead and just press F5 and just let the compiler tell us. Oh, we compile shaders first. Okay. Never mind. So let me just go ahead and do the old. Right, here we go. Okay, I've got LSP stuff, so you know I can just do one of these. Wait, what's going on? Right. Rightio. So, what is right? Free indices. Okay, so now we're going to go into the shaders and let's go full ham. So we're going to look at the So that's the free indices shader. We don't even need a free indices shader anymore. Let's set up the... Effectively, we had a way of... Wait a minute. We might need the same thing for the... How will we allocate... How did we allocate... We bump allocate a single node at a time, isn't it? We need the same thing for... Alright. Slight wind back. We're going to reuse the lovely free indices buffer idea. No. Yeah, we're going to need to keep that for all of the cluster nodes that we have. So be cluster nodes free indices. So this is how we're going to allocate them in the when we copy them over, I think. Because there'll be a fixed size where we're allocating 64 at a time. So we just need a way to quickly allocate basically a pool of these nodes, like a fixed size of them. So I think we'll still keep the... We're still going to keep this because it's a good strategy. So it's the number of like volume nodes. Volume nodes is a terrible name. It's kind of clusters. We don't need to know about the number of spheres. Something like that. Yeah, so this needs the number of nodes. And it's got to be a multiple of 64. So we can do that round up a line. Because it's a power of 2 right hand side, so we'll just do that. Okay, so I'm glad we're going to keep that. So that shader was about to delete. This sort of lovely free node indices initialized. This basically just goes over and if it filled in an array where you could just pop off the end of the array atomically and just get an index back, and you knew with that index the next 8 elements are all yours. But in this case, we're going to change it for 64 elements instead. So we just like we just pre-fill the buffer with like all the allocations. So it's super nice. Wait a minute. There needs to be some division in there. So this needs to be round up to 64. And you need to divide by 64 rounded up. Is that right? Yeah, because you need one entry for each of those. Excellent. They got a visit from the Royal College of Music and play in their concert hall. No, you So does that mean you get to visit the Royal? Ah, cool. Was it really fancy? What to do if the project scope is too big? I've been writing a compiler. Cool. Well, yeah, you just get to a point where. So, there's a couple of things you can do. You can pivot, or abandon project, or keep going. Um, so, your best thing, your best thing to do is like probably pivot if you still want to carry on the project. You know, you have an idea where you're like, hey, I want to do this big thing. You realize it's not capable of doing it. But maybe what you're capable of doing is achieving something smaller quicker. So like I'll give you a bit of a something I'm thinking about. For this project, I want to make sure that I could probably release it. I'm working on it in my spare time. So I don't really have a full 8 hours a day, 5 days a week working on it. And I'm streaming it 100%, which means I'm not really 100% focused working on the project within the hours that I work, right? Compared to if I was off stream. So ideally, I need to keep the project scope small. So chances are I'm going to think of something too big. But the idea is you have to sort of refine that and just be like, what things can we miss out on? Or do I need to think of a completely new idea altogether because this idea is just way too big? And just keep looking around until I've found a simpler path. And I'm sure you're capable of doing that with everything. Like a programming language, it will probably be like, I want generics, I want, some compile time, whatever feature and whatever, which probably adds more complication to the language, number one. And you might say, I want to write, I don't know, VM or whatever, I don't know, just throw random features in there. But the thing is like, do you need that feature to get something up and running? And that's where you can just start off, right? Is get something up and running, and then tune it, and add the features in next that seem most important. And that's how you can kind of really make something very daunting and big actually achievable. I can make a smaller demo version to have something. I started with C language, then started wishing to have methods. Oh no. I realized too much. I don't realize why people like methods so much. It's crazy because people just end up creating like code that's hard to follow. You have like an initialize function. They'll be like, oh yeah, my variable dot init, and you press F12 on it in Visual Studio, and it goes, an init function. You say we have 69,000 of these in the compilation unit. Which one? Which one is it? And you're just like, and you got to try and find it and locate it down. Methods, man. I guess that's the problem with the LSP. But you need some like complicated thing. And when you view code on GitHub, you go, great, an init function. How do I find this? With the GitHub search tool. Or if you don't have that, you go, great, I'll download the code. But you just want to like look at it, It's just way easier with like functions, I find, at least. But yeah, methods are like, they just like destroy readability in my opinion. Dot syntax for LSP. Yeah, but you can do prefix syntax for LSP. I mean, then editors can have simpler implementation. But yeah. Yeah. It's just like methods and namespaces are just pointless at the end of the day. Hey, Soulphone. Radio. Radio. So we're not deleting this boy anymore. We'll just rename it. So this is called cluster nodes, 3 indices, and we only really need this one. Oh. Right, globals. All right, drop that one in there. Doom. Doom. Yeah, so we need to make sure. All right. Oh, yeah, we need to rename those as well. Yeah, we'll come back to this and deal with this in just a second. This is globally accessible data on the GPU. All right. All right. Okay. We'll come back and edit the constants in just a second. I want to deal with this and the CPU side code. No. Cluster node. All right. Damn you. All right. So CPU side, when we dispatch this boy, free. All right. Cluster nodes. Crap. Cluster node for indices. Damn you, plural. No. Right, so cool, so now. Right. Alright, so the CPU side, it says cluster nodes. So this only has to be called once at boot. And it just sets up the array so we can just bump allocate. Sorry, we can atomic decrement off the end of the array and pull out the index. Which is super nice. Right. Awesome. Okay, that'll be compiled in later. So where's the sphere site? Okay, cluster children count. Right, it's divided by 64 now. Ah, that works. Excellent. So that all works now. It's divided by 64. Right, so I should allocate the things all well and good. Right, so let's hop back into the where's the the globals. What stuff can we keep and get rid of? So this is used when we're constructing the volume. So the 3 indices for the nodes now. We don't need a midpoint cursor, but what we do need is the so start index is always from 0, so we don't need that. We do need the number of nodes count, so we can then allocate it at the end. Well, something like that. Yeah, we can tell if it's too big or too small. Don't need these ones anymore because they'll do the sizing. Indirect tiles, we need to keep those. Excellent. So now we can go down and continue with the so I want to do this I want to keep this one right. Construct the leaf spheres. It's still so it's just tunneling down now. Yeah, I think we'll do the ring buffer idea. So I think this is kind of not. We're not doing this all in one part. We're only going to tunnel down. So the tunnel up is in a separate shader, which I've already written anyway. So it's just basically refactoring this to like a ring buffer way of doing it. I think we might need. Why do we need the parent? Because you need to be able to tunnel back up, isn't it? No, no, no. You might not need the parent at all. Wow, that could be powerful. Right, so we can delete the node indices array. The free indices, we're just going to bump allocate them instead. So there might just be a bump allocate. So volume cluster nodes next index, something like that, right? And this thing in the constructor reset is literally just gonna start off as 0. Midpoint cursor can go away. I don't think I need the initializer thing anymore either. Hey, Safon, how's your language coming along? I remember he was building building one too. How's it going? Ooh. Yeah, so in terms of these planned comments, that's only because we're trying to build a bigger one. We needed this sort of standby queue thing as well. Yeah, we don't need any more. Well, yeah, we got this. It just needs to set the root. The problem with the root node is it's just one node and it doesn't have any siblings. It's so annoying. But we'll allocate in its own set. We'll waste 64 nodes. Because yeah, we'll just waste 64 nodes. How big is our node anyway? Do we even size it up? 1, 2, 3, 4, 5, 6, 7, 8. 8 units. So it's a cache line. No. Half a cache line, 32 bytes. The 32 times 64 is what you allocate as the wastage. Right. It's just under 2 KB, 2 KB that we waste. That'll be fine. It's just kilobytes of memory, you know. Bill Gates famously said 64K ought to be good enough, but you know, it's only 2 KB. What's the problem? Yeah, so we clear that, and the nodes count. That's the other one. So 1, because we allocate the... Yeah. Root node. Okay, root node slash... Oh, LOD is 0. Should really be a constant. Over allocate. So that every other node every other LOD has sort of like They're together, right? They're 64 together. In the same sort of... Their 64 starts at a multiple of 64, something like that. Get rid of those two, don't need them. This is the root node. So that's that location. The parent thing goes away, but we've got a different set of things now, right? So we've got to hop into that. Lovely, lovely, lovely. Close that. We've got to just basically settle this up. GP programming at a T. So you'll set 0 and then 1 to 0. The exclusive bit set's the same thing. Child node start index. If there's an invalid index, we'll use. I think it'll just be U32 max. It's not doing assigned anymore. Did we change the signiness? Yeah, we changed the signiness, so it's just unsigned. We was using unsigned because we had this like midpoint cursor and negative was leaf node, but we're not doing that anymore. Right, so that's the setup. Code sorted out. So delete those. Boom. Wait, why are we doing 64 at a time? Voila, first shader edited. So, well, okay, I guess it's the second. We just did one before this one. So this next one is the super lovely complicated one, and it's going to be awesome. But we need a ring buffer that we're going to build in. It maybe just needs to be a ring buffer. Since we can just make it a linear buffer and just allocate enough nodes. It's cool. Right, I'll be right back. I just need to take a quick break, and then we'll sort this shader out. And the beauty is actually, yeah, so you have to remember we're going from 2x2x2s to 4x4x4s now. Cluster sizes. And that's what we've got to change ultimately. And also we're changing it to this new ring buffer idea. Which should be awesome. So I'll be back in a couple of minutes and we'll resume. Enjoy the tunes. Right, welcome back everybody. Let's have a sweet refresher of H2O and then we'll carry on. So quickly, I did on the constructor when we dispatch it. Where's the constructor reset? Where are you, little? This one. Oh, it's fine. It launches the correct number of groups. Why did it mem set to the children? Oh, we don't need the children indices anymore, so we're good. Bam. Rightio. So, what are we launching? So each wave, this used to be a 4x4x2, and it was a really silly thing of 2x2 to 1, 2x2x1 of clusters, because the clusters used to be 2x2x2. So in a wave of 4x4x1 threads, you could fit 2x2x1 clusters, right? But we're not doing that anymore. It's a dumb idea. So instead, we're doing 4x4x4, so 64. Which means you need 2 wave 32s. So you're gonna have 2 compute units processing this, and they won't be in lockstep, right? So you got to do some, like thread synchronization stuff, but it's fine. Yeah, we use C++ for work, but I just pretend it's C. I have to interface with other people's code sometimes. But yeah, at work I've had the chance to kind of write C like, which is great. But yeah, I write in like a sort of a certain style which has been agreed upon, basically. But yeah, we have different styles throughout the whole code base, which is a bit weird. Yeah. C++. I use the odd C++ feature, right? I use templates when I absolutely need them. But that's basically never. I'll use closures when I'm being lazy, like everyone else does, right? What else? Yeah. I don't think I use much. I think I've done the odd inheritance thing as well. Just because I wanted to implicitly bring in some fields in or something dumb like that. So this shader builds the initial shape of the cluster tree with all the leaf nodes and leaf spheres placed down. Excellent. Number of... We don't even need to dispatch data LOD number of them because we're in this lovely like linked list thing. Not linked list thing. Ring buffer thing. So the wonderful thing is thank you for following. So we don't need a spheres. Volume sphere doesn't even exist anymore. Right? Goodbye to you, sir. We don't need a free indices array. That's only when we've completed the construction. We're like, hey, this thing fits in main memory, and we allocate it. Something like that, at least. Then we have a volume cluster nodes, which to rewrite, yes. With the edits, we don't have a construct LOD anymore. That's implicitly done when we go down the tree, I think. Yep, it is. Right, so when we launch this guy, right, it's going to be amazing. So we've brought it down to just 2 buffers in there now. Not that it really matters. Well, it reduces the complexity of the shader, I guess. So we don't launch them, for every LOD, start the highest, go to the lowest. We just do it all within the shader now with some... we need another buffer. Another buffer. We need to have an index of like, hey, this is the next... We'll call it the process queue. So we pop it on the end, and then we'll read from the front, right? The process queue, which basically just has like the cluster, whatever, cluster indices. Easy. So let's just read write because we push and pop in the same shader. We'll have some atomics and stuff, but yeah. So we get rid of all that. Bring this all over here. We probably want to replace this one with the... we need a buffer called process queue. We'll sort that one out. So be the volume constructor process queue buffer ready. So we're going to fill that one in very quickly. So basically we need, based on the maximum number of clusters in a... That's not clusters, I know. Time size of U32. I did it in the wrong one. Right. So I just need to throw that in the data structure. And away we go. So this goes there. This goes here for the synchronization code. Delete those two. We need the global buffer in there as well. Then we do a super lovely dispatch. Same code. The way we dispatch is different now. We dispatch cluster sphere dims. Where the hell did this... Right, let's ignore that and think about what we need. So we've got one cluster per thread group. So how many groups do we need? So we need so basically we need to figure out, now this is going to be quite interesting. Is there a way where we could tell with Vulkan how many compute units a GPU has? And I just want to spawn a full set of compute unit. I want to spawn enough thread groups that will run on compute units multiplied by the number they support to sort of put on hold while they deal with memory access problems or something like that. They can switch out, right? So Vulkan get number of compute units. It's not the number of cores you need to maximize performance, it's the number of threads per thread group. The maximum number of threads the most on NVIDIA is that. Yeah, but that's in a that's within a thread group. That's on one compute unit. That's the limit of the compute unit. I don't know what they're talking about. Max number of group invocations, the total number of count across. No. That's can be quite big. Right, let's go to the stats thing. I'm not sure this person fully knows what they're talking about. Like, pretty sure that's ChatGPT, you know what I mean? Physical device limits. See, they could have. Well, maybe they could have. Someone has like. Is that like some. Okay. Yeah, don't use that number. Yeah, but you can't believe anything anymore. Yeah, I was just joking. It was ChatGPT. Yeah, it sounds like a. I don't know if it is. It seems like. But maybe this could be right. I'm not sure. Is the total thread count across a work group? Total thread count across a work group. Is it really? So what's my AMD card say on that one? Vulkan info. Oh, that one, yeah. 1024. So you got. So AMD hardware's got wave 32, but technically it's got wave 64 as well. But we're just going to imagine wave 32. Like it can run. It's got a thing called a dual compute unit, where it's got two wave 32s which can run in lockstep together. And they're built into the same workgroup processor, as it's called. So within a workgroup, so what I mean by workgroup in Vulkan is thread group or dispatch group, we're gonna call it, right? It's this guy that you define for the shader. So this is the maximum number of invocations. Yeah, so say if you had wave 32. Yeah, but this could be part of the number we need. So we did 1024 divided by 32. If it's 32 times 32 and it's 1024. That feels wrong to me. I thought they had. I thought they had a way of switching out. Yeah, I think on the hardware, they can only be running 10 waves or something like that concurrently. From what I remember reading, I forgot what it is. So they might. Yeah, some of that. Anyway. Because the VGPR count you've got is. I forgot what it is. I think it's 1024 VGPRs per workgroup processor. And they get shared. That's a different thing than this. It's the maximum number of work groups to be scheduled in one dispatch. Right, I kind of want to work out like how many compute units I've got. That's the number I want. And then I'll just like times it by another number. And I'll just dispatch that because I want to just have. I also want to have a full the full GPU just going at it. And I just want to essentially have worker threads. I don't really want um, well, I don't think there's a good way of telling. Maybe we just design the algorithm to be different then. If there's not a good way to tell, like I could hard code it, right? And I'd be like, well, if you're on this card, you're this many. Like you can tell if you know the card, right? Like on AMD 6600, and you can just say compute units. Why don't you just have a look at it? It just tells you. I think it's a bit weird, the NVIDIA ones. We got 28 compute units apparently, right? It's nothing too beastly. So there's 28. Well, it's 28 times 2 because each one of these is a. I think each one of those is wave 64. So there's actually 56 of those boys. So I want to launch a 56 times 10 in a sense, but maybe I could just pick a number and just launch it. Um, let's take a look at some of the other stats that you can get access to and just see what we can just go from there, right? So let's just look at some of the compute stuff. So there is the subgroup stats. They came out in 1.2, isn't it? So subgroup means like wave, wave 32, that sort of thing. I think it's in here. Maybe it's 1.1. Subgroup, here we go. Subgroup size, that would just be like 32, 64, 8, that sort of thing. Subgroup operations and stages, that's not quite everything we want. 1.3. Compute subgroups. Right, this number, max compute workgroup subgroups. This is the maximum you can launch. This might be the number that I want. The maximum number of subgroups supported by an implementation within a work group. Yeah, no, this is not the number I want. Because I think this is to do with, like, if we see the stats for it. Well, what one is mine? Yeah, my one's like 4 gig, 4 giga, whatever. It's a big number. It's U32 max worth. So I simply launch all of that. It's just silly. It's not a really good number to use. I want to know the number of compute units. My 1080 Ti has CUDA cores. Yeah, but what even are CUDA cores? They're probably counting the SIMD lanes. Each element of a SIMD lane, maybe. So maybe you divide that by 32, you'll get the real number. No, it's not. That'd be way too high. Wait, will it? So I think CUDA cores, if 584 Yeah, it's probably right. Yeah, they probably include the SIMD elements in that. Uh, so these two parameters are called GL max compute units, which you queried, or CL, by calling this, um, which indicates the number of parallel compute units on the device. That's what we want in it. As a single workgroup executes on a single compute unit. However, it doesn't seem to be a way for Vulkan. Vulkan has no way to ask this question. No. And it's probably for the best. What? The first concept of computing is not well defined, even in OpenCL. Secondly, if you want to ask how many units can execute in parallel at one time, yeah, that's true. They can execute like, whatever in parallel at some time, but they switch out when you hit a memory read and you need to wait. And they'll do another one. Maybe I should do a different algorithm instead. But it means we can just do one dispatch and keep going the whole way. I could just pick a number, but then it will run suboptimal on different GPUs, which is the problem. Hmm. So, but then if you have too many, I have to start up some and then they'll just have to stop. And you could be over by thousands. You have to start up maybe hundreds of compute units just to stop them right away, which won't be ideal, and they'll have to get scheduled. Um, so we don't know how many nodes we're ultimately going to have. Man, why? So we used to dispatch over. Yeah, we could just dispatch the max amount that we'd need. That's what we're going to do. Right. Then we can move on. It would be better if we didn't have this. But yeah, so we need. So the max that we need, we've got to write this out, is 256. Wait, it's just. It's 256 divided by 4, right? Because 4 in a cluster. 4 spheres in a cluster. 64 cubed. Did we get rid of that other one which was doing this sort of thing? How do these constants out? No, I got rid of that constant that was doing it. Yeah, we need to do this sort of similar thing again. So 64 cubed plus 32 cubed plus 16 cubed. These are all different LODs, right? Is it just divided by 8? Yeah. Plus 8 cubed plus 4 cubed. Oh crap. Is that the lowest you have? Eight, then one, isn't it? So you should have 7. 0, 1, or 1, 2, 3, 4, 5, 6, 7. Excellent. So we need to add all those together. So that's how many. That's how many clusters we're gonna possibly process in total. So we have to basically overlaunch that. We was gonna launch that many anyway. Yeah, I was gonna have to launch this much anyway with the old method, but I was hoping to do a better method where we could just tell how many processing units we would need. Um, um, maybe there's a certain number we can use. I'm not kind of fan of that one. Maybe it's checking the Vulkan header. When was that comment made? 2019. Been time since then. Maybe it's something in the header that got added, which I don't. By some, I don't know. I didn't see it. That's just quite a hard thing to search for. Is there any other sort of questions, similar questions? Um, Right, it's just CUDA. Um, because the thing is, right, if on, just to compare the sort of numbers we're dealing with here, we'll over execute far too many. If you add all those up, right, so maybe it's like, I don't know, let's just say 400 odd thousand or whatever. I don't quite, maybe it's less than that. Maybe let's be generous and say let's be generous and say it's 400,000. If we have 28 compute units on this machine, which have, well, it's actually 56 because they're wave 64, but anyway, so they're wave 32, two wave 32s. And then say they have support for like swapping out to 10. If they hit a read where they don't have it in cache, they'll swap out to another shader and carry on there. So you have up to. I only need to launch 512. So 560. To get full. Yeah. Full utilization. So I could just pick a number, but yeah, I'm off by like a factor of like, like just crazy amounts. Like I only need. Yeah, so maybe I just launch 2000, just be done with it, and just then it's scalable for current hardware, I guess. But On the low end hardware, we'll be launching too many. They don't have that many compute units. So I can look at those other numbers and see if I can gauge something from that and just sort of intelligently select. Like do a kind of like a best guess, right? Properties, that's what I want to click on. So it's compute units, invocations. So I think I had 1024 on mine, right? And they do sort of scale up to something kind of sensible, right? You know, it's not like there's only one of them which is ridiculous. So this is within a work group. Right, let's read that number. Or sorry, read that property. What does it mean? Is the maximum number of compute shared invocations in a single local workgroup, which doesn't mean like the whole device in any way. Maximum number of local that can be dispatched. Yeah, so what I might do is hard code a number for now, because I like the algorithm for this one. I'm gonna hard code a number, and we'll stick it to do, and we'll just have a table, and we can just punch in some numbers, and maybe it could be a tweakable thing in the settings menu or something like that, and just it could maybe yield better performance if it's modified correctly or something. I don't know. But for now, we'll just say like number of compute units. So there's 56 on this card, and then there's a number of I forgot what word they used. There's a way of like number of paused compute units that you can have, basically, right? Number and maybe let's just say there's about 10. I forgot what the number is, but then you have like you'll have a certain number of total compute units that you can run, right? And it's just this multiplied by that. So I'll put a big old fat to do in there and just say like to do get this information from the backend, right? With sort of lookup tables. It's the best we can do. Yeah, with lookup tables and make it overridable. By the user in the settings, right? Maybe we can, yeah, I don't know. But that should be far better than having hardcode what we have. But anyway, so we've got this number now, and we just want to launch. Like, so given that, like, we just want to launch across the X. So we just go, so across the X-axis, just launch that many, please, and just fill up the GPU with compute, but not fill up too many. That's launch too many waves, right? Afterwards. Okay, so we'll play around with that number and maybe improve the results. Okay, so let's get into the meat and potatoes of this. Yes, we did the sync code for the process queue as well, and we're good. So we go into the meat and potatoes of this guy. So this shader still builds the initial shape of the cluster tree with all of the leaf and leaf spheres placed down. Yes. We don't dispatch this many counter for them now because we changed the algorithm. We just have this sort of process queue that we're pushing and popping off. So in the we need a Wait. One. In the globals, we need a process queue. Process queue head, index, tail. And we're just gonna process with the head and push on with the tail. Yeah, we'll bump into the problems with that. So when you start a build from scratch, we need to initialize both to 0. They have nothing on there. Well, they have the root node. And we'll maybe push the root node on the queue as well. So I should probably stick that in the process queue. We'll pin entry in there. So here, we'll do a BC process queue. I'm going to put on the root node index, right? Put the root node on the process queue. And voila. So we need to actually quickly just change the CPU side here and just put that process queue in there and do the synchronization code. Very nice. Cool. So let's move on. Back to here. So we delete that line there because it's pretty dumb. So each wave 32 is a 4x4x4. No. Each dispatch group, or thread group, we're going to call it, is a 4x4x4 cluster. Right. Or processes a 4 at a time, right? It takes a job or a cluster from the process queue. It takes a job from the process queue. Each dispatch group takes a cluster from the process queue. And sort of runs the list of edits and sort of evaluates the list of edits, something like that, right? Yep. Each dispatch group maybe we'll just do this. And then it we'll push its children onto the process queue if it has any. Cool. No. However, this shader does not finish the following aspects: create lower LODs, simplify the tree, and the nodes will have allocated children. They might not have any of their own. Why? Is that true? So you'll go down... Yeah, because you might fully delete it or something. Yeah, that's true. Right. Excellent. So let's write the new sort of loop, and then we'll figure out the rest of this. So let's just start writing something new, and we'll pull from the stuff below, actually. That's the way we'd do it. So this is kind of the code, right? So we don't need the tunnel down thing anymore in this, and tunnel up. We're always tunneling down. So the idea, let's just start here. So we're going to say like while, just a while loop to infinity and beyond. Then we have another while loop with another infinity and beyond. Well, yeah, they obviously both stop sometime. I was going to say we have a maximum number of processed nodes. That could be a thing that we do. I was thinking about having a much larger set, but maybe it's fine to not have that anymore. But we can always think about adding that. If the process queue has a job, then take it. So we're going to keep spinning until we can take it. Yeah, that's the plan. So we'll probably just spin, because basically the idea is yeah, I think we'll just spin. Yeah, because the other algorithm would have just like started a bunch of wave 32s and then stopped them right away. This one just keeps the compute units busy, and they all stop when they've run out of work. So we basically want to say like, okay, well if GFX global, and we've got to look in that global thing because I forget, but it's like, hey, if the head is I got to figure out how we do this atomically. Hey, if the head is equal to that, just continue and go again. But I kind of forgot when I did an atomic load. Right, so we'll just keep doing that. But if we get a chance to take, so the thing is about GPUs. It's another thing about GPUs. These things, they're just, you know, as Peter Griffin says, they just grind my gears. For some reason, compare and swap, it's just not as good as the compare and swap on the CPU. And I hope it's not going to bug me up. Right, so why don't you get back again? There's some you don't know. You don't know if it was successful or not. I think. I'm pretty sure that's it. It's let me see the HLSL one. HLSL atomic, or maybe I need to look at the GSL. I think there's something really weird about it. So you have to compare, so that's yes, you have the bit of memory you pointed to, and that's the thing you're comparing it with, and then that's the data you're going to put in there if they end up being the same. Then you get back the old data, I think. So let's just read over what that means, or what they're saying it is. But we've got to see if this is a problem for us when we're trying to pull from this queue. Maybe you can tell if it's successful if you check if the compare is the same as the return. But I think you might have instances where, yeah, I don't, like if we're trying to add one. Anyway, let's just see this, right? Let's just read it. So performs an atomic operation of compare, right, with mem, right, as we said. If the contents of mem is equal to compare, then the content of data is then written. Otherwise, the content of mem is unmodified, right? The function returns the original content of the memory regardless of the outcome of the comparison. The contents of the memory being updated by atomic operation are guaranteed to not be modified by another assignment or atomic memory operation in any shader invocation between the time of the original value is read and the time the new value is written. So here's what I want to try and do. I want to try and like add 1. I want to try and add 1. And be like, hey, I'm the guy who added 1. Right? So I want to be the guy who sort of incremented this by 1. And no. So if you say head plus 1. No, if you say head index, and then I say head plus 1, and this returns head index, I'm the guy that did that. But then, no, but it returns it regardless. This is the problem I'm having, right? If you pass in compare where you say this one needs to be head index, and this one you say is head index plus 1, you'll get back the original value, right? It says here, if the contents of memory is equal to compare, then the content of the data is written into mem, otherwise it's unmodified. This function returns the original content of mem regardless of the outcome of the comparison. So if it fails or it's successful, the original content is returned regardless, right? The original content. So how can I tell if it's been written to or not? Surely someone else has had this problem. Maybe I'm just thinking about it wrong. The contents of the memory being updated by the atomic operation are guaranteed not to be modified by other assignment. Right, so if it fails, so it's only going to fail if someone else tries to do it, right? Let's think about it. So it fails because it's successful, right? If it's the only thread that comes in here and the compare ends up being true. If another thread came in and upped it by 1 and it returns the original back, then you'll get you'll get head plus 1 or whatever from there, and it would be different. So I think it might work. It might work, right? I think it's fine. Because, right, let's write out in our code and we can see it, right? So we get this sort of OG head index, right? So we need it's a similar sort of thing here, right? We get the address of this guy. The value we expect it to be is this one. So we expect it to be this guy, and then we want it to be head plus 1, right? So we are able to take this if OG head is equal to head index, right? And then we can break, and then we can just use that. We can take the that is our next. So we can put in here our cluster index to take, basically, so to speak. Hey, the cluster index is equal to BC process queue head index, right? So let's just think about this. So if you do a compare and exchange and you're successful, you're going to pass in, you're going to compare with that, and you're successful when the value you're pointing to is equal to that. And we're going to say when it's successful, make it head plus 1. That would mean this. That means this would return the original value, which is that, right? So they're equal to the same in the score. So if it fails, right, and this is not equal to what that is, you would get back something that's different. Yeah, I think that's fine. I think it does work out then. Right. Okay, that's good. That should be fine then. So we can actually use that then. I misunderstood this function. So you have to do the comparison yourself to find out afterwards. So then this means we've got the cluster index, right? So we can get the cluster node. So I think we can, like, the plan says, hey, I need to build like a separate list of edits or whatever. For the first version, we might skip this, and we're just going to make the shader slower. But in future, we can speed it up when we add more edits. We'll make it so we can reduce the amount of edits every single node is going to process. But for now, we're only testing a single edit, so it's not going to be a problem. But for now, then, wait, so we do, yeah, do over every single edit. Okay, this is good. So now we just need this code. Traverse down the tree, but no, it's not it. So we need something like this code here, and we're just going to change what we need. So this goes in here now. Yeah, we need a way to terminate the threads. I did kind of underlook that problem. How do we terminate? We should be able to terminate the thread here. So what I want to do is if I get the head index and it's equal to but how do you know when to terminate? Because they would all end up on, like, you probably wanted like atomically increment, say, hey, I've got this many threads waiting. I think you need a global. We need to put this in. So it's like, oh, this is how many cluster, this is how many dispatch groups waiting count. So I think that's the easiest way I can think of. So again, in the this go is going to have to reset them. So reset that to 0. When they go into here, we're just going to add it. So let's think about this, right? So as soon as you hit in here, you add. Wait, as soon as you hit here, you go atomic. I'm not sure if this is true. The thing is, they'll all be waiting. Like one thread should have taken Like, so ideally, right, you get here, and you just sub 1, right? You need to have a way to exit, but so if all of them are waiting, then you can just return. But where can you do that? Here? I don't think that's right, but let's just write it out anyway and just think about it. So if that is equal to like BC dispatch groups count, which we've got to write in there still, then we'll just return. I don't think that's right because you could, right, so you've read here. Yeah, you know, that's fine. Because by the time the last guy comes in here, he was the last chance to add any more work. But he's not adding any more work. Yeah, so as soon as the last guy comes past here, this then can trigger. And you do an atomic load, by the way. That's good. I like that a lot. So that's how you terminate the threads. So we just got to add one of these boys in here, a nice little integer, to just to say how many dispatch groups we got going around in a little oh, where are you, bugger? This one. Number of total compute units. Right, I've just thought about this for a minute. We've got we need two wave 32s. Divide by 2, sort of, you know, we need 64 threads. Divide by 2, as we need 64 threads. As we need 2 wave 32. We need 2 wave 32. Divide by 2 is we need 2 wave 32 for our 64 thread dispatch group. Yeah. Boom. Boom. Right, so now we can carry on and actually get this sort of processing thing working. So it's very different in the way we... Right, alloc child node. Ah, we didn't handle the thread group thing in this. Damn it. So only, like, you're literally doing 64 threads at a time here. So what you need to be doing is you need to be saying, hey, if, and you need to like then read lane, do a read lane on it. So you say if sv dispatch group dispatch local index. So if that local index.x, because you should be how many did it dispatch? So dispatch number of compute units, that is wrong. It's that. No, I'm just looking for local index 0, aren't I? Yeah, so the first thread out of all of the... Yeah, then you do if you can't do a read lane, you got to transport it across the LDS. You store an LDS, read it back from LDS. Because it's across two waves. They could be in different yeah, they're in different waves, isn't it? So you can't what was that noise? Yes, they could be different anyway, so I've got to do something really silly. Which cluster? It's no longer a thing. Right, let's change how that works. So instead, we'll poke that in LDS that's shared between the it's work group memory, isn't it? But yeah, it's dispatch group memory shared between the two waves which run in the two waves that are running at different times. But we need to make sure that we kind of stop them here. So there's a way to do that. We call it a control barrier here, but we just need the control barrier dispatch group. We need to wait for the atomic mutation operations between all threads across all waves, across all waves that run in the dispatch group. Yep. So obviously just the two waves need to, get here, and then after that, like, because the first wave is gonna do all of this, right, by itself, and the other wave is just gonna get here and then park, right, and then so the first wave is going around here, eventually gets its job, breaks out, or it sets that thing, breaks out, right? So you then get this cluster index by just reading from there. Now, you probably need to use atomics. I don't know if I tried atomics. Hopefully my compiler works on LDS. We'll see. We'll find out. Okay. So that actually solves the problem. Now we can do the rest. This does the processing. So, right, what do we want to achieve? So, when we process the cluster, we've got an array of edits run over. They're going to color in the spheres basically, and it's just going to be a bit set that we care about. We don't really care about the material, because that's a separate thing. So allocate. So go back to the plan quickly. Is there a boiled down version of this? Yeah, so we just avoid making the other list, because I can't be bothered to do that. And we need to know if the child of a boolean, see if we can make the that's optimization, isn't it? Yeah, we need the boolean to say allocate child though. If any child knows return. And it shows the process queue. Right. Let's move this tunnel up thing. It doesn't make any sense now. Place sphere down. Right, okay. Excellent. Here we go. So, we'll still need this alloc. We don't need the leaf node thing. We don't need this absolute cluster node index either. So instead, yeah, we just fish out the node. We've got the node. I mean, we have, so it's volume cluster node, and there's our node. Right, this is just some printing stuff. I need to worry about that. So we go over all the edits, blah 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 blah. Process all these guys. So it's basically center position, half dimensions. We do ellipsoid or cuboid, and it's supports rotation as well. So that's all this code is doing, basically, is checking to see if this grid cell... Oh, interesting. There's some stuff here that's not quite initialized, maybe. Here we are. So let's take some of this stuff up the top and figure out what we need. So this one's needed in there. This one's needed in there as well. This one's needed here. All right. So basically we need to process this now. As soon as we get that cluster index, we know. Maybe. No. Right. Cluster index, yes, that's its own. You don't, but the cluster sphere index, local times mod 4. Damn it. What's a slice now? It's 4x4, so it's 16. Plus mod 4. A row is 4, so and then mod 4. So 0 to 63 incursively now that we've increased our size. Sorry, inclusively, that's what I meant to say. Yeah. So right, I think this stuff all stays the same from what I remember. Wait a minute. This needs to be moved here because the LOD of the cluster, because we would have set the LOD of the cluster, so we can get the LOD of the cluster here. So you want to get the cluster LOD. Maybe we kind of do need it, so it's probably best just to sit there. Volume cluster location LOD. Wait, where have I read the cluster? Maybe it'd be nice to do some bounce checking. I don't know. So there's your LOD. And we can use that. That's the one that we're constructing. Let's construct LOD. So you could have painted down at a lower LOD, and this just has a way of shifting the low level of detail coordinates. Wait, is that right? Yeah, that has a way of shifting down the coordinate of the cluster into the highest LOD coordinates. So the lowest LOD would be like, I don't know, 1, and the highest LOD is, sorry, the lowest LOD dimensions is 4 cubed, isn't it? Right. Whereas the highest LOD dimensions is 256 cubed. So it shifts from that space into the other space. Right. And it gives us our sphere radius as well. I don't know if this will be correct. Let's have a think about this. Let's have a rundown. Construct to highest LOD diff. So you got 7 now. So 7 take 1, 6. So you'd be at... Yeah, this is alright. This is fine. Coordinate at highest LOD. So say if you have a coordinate of 3 and you're at LOD 0. So you've got... Sorry, coordinate 2. So you're like... So you say if you're like... this one. Right, 3 across, 3 up, and 3 going in, or whatever, I don't know. Whatever it is. So, when you... for the LOD diff, so say if you're going to the next... You go to the next level of detail, what do you expect to be at? That's just going to times it by 2, isn't it? It's going to double it. So, if you've got a 4... So it'd be 4 on the first LOD, 16 on the next LOD. So if you double your 3, you only get 6. That's not right. But if you did 3. Do it times by 4 then? Is that the plan? You get 12. Right, so 0. No, it wouldn't be 3, sorry, it'd be 2, wouldn't it? 0, 4, 8, 12. Yeah, that makes sense. So you need to times it by an extra 2. So so it's no longer a shift left. It's really like it's another shift left in it. Something like that. Okay. So LOD sphere radius. So if you've got this so the highest LOD needs 64 clusters across, right? Because 64 times 4 is 256. So the sphere size at the highest LOD is 1, right? Then every time you increase or decrease the level of detail, it doubles. So okay, there's 2 spheres then. Wait, no. It's not doubling anymore. Isn't it like quadrupling? Because you're getting your cluster each has a child. Man, I worked out my LODs wrong, didn't I? The number of LODs I need. Shoot. I only need 7. Like, how many times? There's only going to be like 4 LODs or whatever. Is that right? Am I thinking about that right? Because each one of those has a child. You're only going to have like 4 LODs. Whoops, is that right? That'd be dramatically less. Because I was thinking about it in like an octree form, wasn't I? That's why. I was doing times divide by 2. That's not right anymore. Because the first LED has 4 spheres across. Next LED is 16 across. Then 64. Then 256. So there's only 4 LEDs. And then there'll only be 5 LEDs for 1024. Huh. I'm only gonna have 4 LEDs now. Interesting. That makes building the... Maybe we do the octree again. But then that's too many nodes. Hmm. But that makes painting the bigger spheres like less, like they're 4 times as big. So they're going from the size of one, like so you're 256, and then you're like 64 in the next LOD. Um, yeah, so that makes them the size of four big, right? Then you've got 16 big, and then it really does define like what you can do with that. So imagine you have a sphere like that. Then you have one that's 4 times as big. I don't know, it's a bit more than four. It might be better with a bit of graph paper, you know. Um, right. So, I don't know. Can we do like I'm trying to figure out how you even do an arc. Can you do like sine? No, that sine's the. Um, how would you do that on this? But anyway. So your first sphere would be like that. Your next sphere would be out here. Be massive. How would you plot this? So x is maybe it's sine x and sorry, cosine x and sine y in it. I forgot now. How would you even plot that? But anyway, maths ain't my strong suit today. So you get one there like that, and then you do another one like that. It's 4 times as big. Like it used to be supposed to be 2 times as big, which you could work with way better. Um. So um. Right, let's go back to the shader. Let's run some numbers. So you've got this cluster. Say if you to make an octree again, right? It's just going to be you've just. So how did I calculate the number of nodes in it? But I used to have 128 cubed. It's kind of wrong. And then I've said it's 64 cubed. Well, it is kind of that if it is fours, right? This is the highest LOD. But it's kind of wrong because it needs to be the sum of that added up. But it has decreased it. from 128 cubed to yeah, maybe we do the octree thing. Thinking about it. Because then you get more LODs back and it's just easy to work with. Octree of children. Probably better. So this number is actually wrong. This needs to be like some x or I. Some I equal you basically want to iterate to 6, wouldn't it? Inclusively. And you're basically saying 1 shift left I cubed. I think it's something like that. So you're saying so 6, like 1 shift left 6, 64, right? Yeah. So we had those numbers written out literally a second ago. Let's go and grab those. Wrong file. Is in here. Right here. I swear those are the numbers. Oh, why do I need these? Here. Is that right? Two cubed is 8, innit? Yeah. 3 cubed. Sorry, it'd be 4 cubed. So we start off on 1. Yep, that's right. Okay, so let's sum all these guys together. So 3, 2, 7, 6, 8, add 4, 9, 6, add 5, 12, add 64, add 8, add 1. So that's our number now. It's still dramatically less than we had. Is that right? Yeah, because we've missed the, I forgot the old number used to be, but it is definitely less. We do a get diff and find out. It's right, so the old number used to be yeah, but we deleted the children count. What's going on? It should be oh, there you go. Right, the standard does the right. Yeah, so we used to have that used to just be the non-leaf nodes count, that number. Being out, we used to have the one up from that being all these leaf nodes, and that is an extra 2 million more. The beautiful thing is we oh, there we go. Let's get my phone back on charge. So we're still saving out 2 million nodes, so that's great. Okay, so now the spheres count is this, and the children count is actually back down to 8. Since we're doing the octree, so we'll go to the volume thing. So with 8 children, we could probably store, sorry, volume cluster, that's what I wanted. We could probably store, so we can do the 2x2 downsample thing again, which is pretty cool. I do like that. So the children bit set, all we need is 8 bits. Unfortunately, we can't really get those bits anywhere. We need the 8 bits. Only using 8 bits, right? We cluster nodes start. Yeah, I think we'll still do the 8. We'll just allocate the 8 nodes. It's fine. Cool. So we don't have to change anything because we've got the constants. But this stuff that we changed here, we can now undo that times 2, and it should still work the same. So save your LOD 0. You're going all the way to the highest LOD. The difference would be, so you've got, how many LODs now? Yeah, 7 LODs. So 6, take 0, you go in 6. 1 shift left 6. 64, and then a half. Is that still right? So it'd be 32 for the radius of a sphere. So given on the highest LOD, on the lowest LOD, you've only got one cluster of 4x4x4, right? So if the space is 256 cubed, and each sphere represents a quarter of that, right? A quarter is 64, right? Yeah, and then half, and then it's a radius, so it is half of that. Excellent. Just 32. Bam. Legendary. So now the idea is we want to. My phone's still charging. Right, it's charging. They're all good. So now I can carry on. This was doing some print code debugging, but we'll carry on that later. Right, so I'm glad we got all this back. This is good. So you go over all the edits. We process them, see if we've intersected. If we haven't, we continue to the next edit. And this is the whole sort of like doing the processing. This is saying, hey, if the target LOD, it's this construct LOD thing we need to swap out. So that needs to now be like cluster LOD. A lot of this code is just going to go, I think. So if the target LOD, so the one we're painting down, is less than, right, ideally you wouldn't even reach this in the optimized version. And it's equal to remove. Right, yeah, we're not doing that logic anymore. We're going to delete this. So this was basically saying like, basically the edits. So you could have like painted over this as some higher LOD and had a higher LOD sphere. Yeah, so you could have painted down some lower LOD spheres like these guys, and then later on you came and wrote a higher LOD here. So you just basically don't need these low LED ones anymore. You could just deleted them. That's all that was doing. But now we're making it so they can coexist. So you can have the low level of detail one around the smaller ones, and it can be some sort of artistic choice, right, when you're making the thing, which is cool. Yeah, they kept paying. That's what you benchmark on Discord is 5 ms too high. Seems like a lot. What are your goals for the new rework? Basically, yeah. So it is a lot, but we need to like budget basically. So we might end up have a system. See here how we sort of we're doing this sort of taking from a queue, and I think in the comments in the docs I put initial plan. I put hey, if the process number queue is bigger than the maximum clusters to process, then we'll terminate the threads and just stop here. We might put this thing in, and this will allow us to basically say, hey, if we want to run at a 60 FPS frame rate or even higher, we can budget like, ideally on, well, not even that. We can have a graphic setting to say, hey, how fast, yeah, I don't know how I quite want to phrase it, but, or how I want to implement it in the final thing. But the idea is there could be a number which can decide like, per frame, spend this much frame time, actually trying to generate new volumes. But maybe, depending on the game, we just do it at some loading screen, and then the time doesn't actually matter. You do like one per frame, and just fire one volume per frame, and just build them all and put them all in memory. And if they all fit in memory just fine, then that's okay. But we might stream some in. So if we're streaming some in, we'll need like we'll need to have a way where we can control like maybe we can only process, I don't know, so let's say 100,000 clusters per second. So if it's 100,000 clusters per second, and we've got 60 FPS budget, we divide by 60, and that's the number of clusters we process this frame. Yeah, I need to kind of finalize on that one, and that's how we'll decide. Yeah, that's how we'll decide how to sort of work around those high numbers, because it is going to be a high number. But I want to compare against the previous. I want to write a very with this rewrite. I want to see how we compare with the same data. Basically, that's why I've taken that screenshot. I'm hoping to get less, but we'll find out. But we haven't. The 5 ms seems way too much because we're only painting one sphere down, and it was taking 5 ms for like this shader at the highest LOD, which was really bad. So we should be knocking that out of the park with this new rewrite. I'm not sure how it goes. We'll see. But I'm very thankful for this, that this rewrite doesn't seem like a massive redo. It actually seems to reuse like basically 80% of the code. It's just a refactor doing things slightly differently. We're either changing the outside of the sort of the main loops of the shader and keeping the inside bits mostly the same, or we're simply just changing the inside bits because we've updated the cluster size to 4 cubed instead of 2 cubed. So yeah, and that's the other main thing with the rewrite is the we've increased the cluster size so we can occlusion cull more, basically more effectively, and have less nodes to process in a frame when we try and render them. So it should be able to occlusion cull a lot more spheres. So the target LOD that we're painting down is bigger than the cluster. There's a thing we had in the comments. What was it? Yeah, then append it to the array and mark this child as, yeah, so we just want to mark the child as is sphere exists, remove the sphere. We're not doing that anymore. Delete that. So just marking the child. We don't need the is leaf thing anymore. Good. Then this one is basically saying, hey, they're equal. Because they're equal. Yeah, it's gonna be awesome. I'm happy there's not gonna be too much more work, and it's just a little one. So you know, small refactor. So here we want to add op or remove op. So in this case, in the plan, it was saying, you know, apply the affected spheres, right? So we're no longer adding spheres, right? They're just a bit set, right? You got your cluster node. So basically, we need this in LDS memory because you got two wave 32 running out of sync here, right? So you can't. Well, you could store these in. You could store these in VGPRs. So basically local variables, and then commit them into LDS at the end to synchronize, pull the other one out, and pull the other one out, and then what else? No, put them both in there, and then the first thread sort of just stores it in the final allocation or whatever. So you do a 454/2 or something. Yeah, I think it works out just well enough. So we'll do a little local. We'll have a little local children bit set. Why are you in children bit set? Sorry. Wait. Spheres bit set. And this will be, and you put a comment to say this is a 4x4x2 for this wave, right? For this wave 32. This is later sort of this is later combined with the other wave 32, right? So that's really cool. So I don't have to sort of use LDS memory while we're doing the loop and use atomics and stuff like that. We can just be chugging along, you know, by ourselves basically, which is super nice. Same with the exclusive LOD spheres. We'll put those in there as well. Exclusive LOD spheres. Same thing again. So the children bit set, you just need a 2x2x1. No. It's an octree. Yeah, 2x2x1, that's it. So you need the children bit set. Wait, alloc child node, you have that there. It's not one per... Damn it. Wait, what am I thinking? I'm thinking in like in terms of like in registers, but yeah, you need boolean. Has sphere equal false. Has exclusive LOD sphere. So I'll put the comment here. You know, maybe the comment's just gonna be confusing. Yeah, well, anyway. So what else is in in the plan. So we say that we've found. So when we do an add now, we don't place a sphere like this. We just go, oh, has sphere equal true. Now it totally depends on the edit thing, because on the edit rate, I wanted to do something where we can say, let's just drop a bit, is exclusive anyway. This has already got to be sorted out proper, but the idea is you can paint it exclusively for an LOD, and it always yeah, so you can make the lower levels of detail be a bit bigger and wider in areas that you want to. So you kind of just want to say if edit dot is exclusive, cool. Very nice. Then we don't need a child node as it is a leaf sphere. Is that true anymore? No, it's not true anymore. That's fine, because it'd be an any across a 2x2x2. That'd be alright. Then a remove. This one is, you could be removing the exclusive LOD sphere or the... Yes, that just set it to false. Right. Greatly simplified. That's really good. So I think we're at the end now. Now we do the... right. So I need to combine the bits. So I guess this is where I put my comment in. So you combine the bits into a... So you do like a wave... It's like a ballot or something. I don't even have a ballot. Just figure it out. What do I want to do? I want to get back... you see the OR. Yeah, okay, I just remembered. You can just do a ballot manually. You just shift it by the... You shift it by the local index, modded by 32 or something like that. So cluster sphere index, perfect. Gonna be amazing. So basically you get your bit set. So you get your spheres bit set. That would be wave active, which are all active anyway. Wave active bit or U32 1, and it's already, so you'd use the sphere exists. Oh, is that what it was called? I don't know. Has sphere. You use your has sphere variable to be 0, 1. Then you shift that by the index. Bear in mind you've got to mod that with 32 because you don't want to go. You don't want to use the. You want to repeat it twice for the wave. Each wave 32. Where's my tunes? So that will produce you a 32-bit bit set. So I'll put the comment in as well. That comment I had. End up deleting. Oh, wrong one. Exclusive LOD spheres bit set. What are we making? We're making a an LOD cluster system for a game. So the idea is you can build models out of spheres, and we're trying to render kind of as many spheres as possible. That's the plan. So we've just been designing we've designed an LOD cluster system where you can make like body parts out of spheres. And the idea is they can be boned, right? So you can do skeletal animation with them. So we're just working on the system that creates sort of some 3D volumes filled with spheres. So just editing that code now, basically. So we're basically saying like, get the wave 32s. Give the wave 32s sphere bit sets. So you work these, and you might have to do a thread group wait here, right? Because what you want to do, no. So you poke it in the then you poke it in the LDS memory to share it over. So you got the sphere bit set. Yeah, you need to. So it's already been allocated. So you don't actually need it. So you've got the node index, right? So you just set the node up now. That's the code I need. So I think we could just, go and put that in there. So I think the thread group goes here. Thread group wait. So you wait for the two waves. Wait for the two wave 32s before we continue. I guess do you have to really wait here? Yeah, do you really have to wait here for that? Maybe you don't, because it just goes around and gets the next. You should be alright. Okay, so you fit in the cluster node. Right, so these are the boys I need. So the one that really needs to put so what you kind of want to do is you want to say if it's this line of code here. If with the first thread of the first wave, do the single threaded writing. Probably take all of this then. And we have cluster indexes. Now you've got to do this sort of location thing correct. I did kind of forget what that was. Somewhere here in it. This is the previous code. It might be something like this. No, that's allocating the child node. Wait, you might already know what you are. When you allocate... No. Wait. Yeah, you've already had the LOD set. You've got all the threads going. You don't need to set the lock. The children bit set, you could definitely make that. It would need to be combined though. You need to do an atomic OR. Where's the children? Yeah, we'll work that one out. Wait, where is it? Alloc child node. So that is a bit different. You've got 2x2. You got an octree, right? So you're 2 by 2 by 2. So these all share the same one. So if any of those bits in a 2 by 2 by 2. So it's a little bit of a weird thing, but you kind of want to make the bit set. So you want to make it like a children bit set, and then you want to kind of like shift it down and OR it over it. So this is like so it targets that. It was bigger than that. Sure, I guess. So alloc child node. Then you want to build a bit set where you can press. I think it does a sort of a, yeah, it does a slice. Yeah, it's a bit of a funny one. Like you want to know your sort of cluster child index or whatever, and I think you can just OR it into the same place. So you could probably work that out in some intelligent way. So child. I think it could be quite easy. So, wrong one. So I think you could do a. So this kind of your day job? No, not this one specifically. I work full time on a studio somewhere else. But it's just some spare time stuff that I'm doing to have some fun and learn some things, and also hopefully create something of my own as well. That's the plan. Just more of like a little long-term thing that I can dig away at for a few years and have something. Also, maybe have be good for like just future, CVs, that sort of thing. You know. So just a multi-purpose project, really. So ideally, you've got like bit 0, 1, 2, 4. Sorry, been an idiot. 2, 3, 4, 5. So 1, 2, 4, 5, and then like the plus whatever one of that. So those ones are all part the same. So if I divide them by 2, they'll land on the same one. So these two land on the same one. These two land on the same one. And then they're just sort of. So you have 0, and this is like 4. So it'd be 2. So it'd be 0 and 2. and then you got like a whole slice. So six, so it'd be 0, 2, and 8. And then it'd be 1, 3, and whatever. So I think, yeah, they will have the same. Yeah, there's some bit tricks you can do to get this to work. So if I flattened it out, so that's the flat index. So divide by 2, you've combined the ones that you want to know about. Then basically I need to fold the y into the same one, and then I need to fold the z into the same one as well. So 4 and 5. Sorry, it's just a 2, isn't it? So I'll just take 2, I think. I think that works. No, not take 2. What do I mean? Or maybe I can shift it down and then OR it over. No, it doesn't work. What I want to achieve, so that'd be 0, 2, and 8 and 10. They're all part of the same. They're all the 8 spheres which will belong to child index 0. I need a way to sort of fold that in. So I've got numbers 0, 2, 8, and 10. I need a way to sort of make these guys be index 0. 1, 3, 9, 11 to be index 1. Can I just mod it? Is this just a model way? Wait, is that just feels wrong to me? You should have. Yeah, something's a little bit off. Yeah, no, because they're shared, isn't it? Whoops. Oh, crap. So it'd be 1. Where are you from? UK. So 1, because we found it divided by 2, right? So 1, 3. That was right when yeah. Then add in 8. It's 9, isn't it? And 11. So all these ones then. 4, 5. No. 4, 6. Then 4 plus 8, wasn't it? Something like that. It's 12. I don't know if that's right. Yeah, it's because there's another one. And that would be. I think that's right. That'd be 5, 7, 14. think we're off by one still. No, maybe that's right. That's weird. Right, let's double check. These ones are right, aren't they? Because one... Right. Um... Three. Then behind it is +8. Or because you get 8 on a slice. So it's the ones behind it. Right. Okay, this +8. So that'd be... Yep. 9. This +8. 11. That's fine. So 4... 6... And then it's +8. And +8 on the 6 is 14. No. Yeah, 14. 13 and then 15. That's correct. Okay, these are the numbers. So I've got to find a way where I can sort of give this one index as... Wait a minute. It's 3D. Then we need another... Wait, what have I done? Wait a minute, have I just thought about this wrong? It's not an octree, would it be a... Oh, no, it is. Yeah, so that's one slice. So you need to repeat the same logic for like... so we need to add like 16 to each of these. Man, it's so confusing sometimes. So there's a pattern in which that we can flatten this out into... So these are our numbers which should get the indices of like, you know... So this should get index 0, rise equal to, you know, 1, 2, 3, 4, 5, 6, 7. So these indices should come from these guys basically. So we join them all up. But yeah, how do we do that? So we divided by 2. Yeah, divided by 2, and this gave us, so sphere index divided by 2. So there's a pattern here. There must be a pattern here, which allows us to, so we could, just gotta find it. So 1 is your x. Yeah, odd numbers are x, because they're like 1 plus, basically. And your y is... Yeah. So your you know, your x requires like one step, 2 steps get you a y, 4 steps gets you a z. So we could take we could mod. See, maybe I should just do it in the regular space, but maybe we just mod 16. That'll get me whether or not I'm 0, 1 along the z. Or just greater than 16 or whatever. So 1 and you multiply that by so it's 2 by 2 by 2. So just multiply that by 2 because it's 0, 1. Yeah, but it's a slice, so it'd be 4. Then you want to add cluster sphere index. Now I need something to say whether or not it's on a certain y-axis. So that would be, you want to know whether or not you're, what are you saying? You want to know if you're greater than, well, you can AND it with, you need a slice of, so 16, that would be 0x, that's 7, isn't it? Wait, sorry, no, yeah, that's 7. That gives you maximum number of 7. No, it's 8 in it. Yeah, 7. They get a max number of 15 or something like that. 0. I think that's right, isn't it? So you're 1 shift left 4. What do is? Yeah, 1 shift left 4. Gets you 0 to 15 inclusively. So with that, you then just need to tell, so you're keeping those bits, then you just need to tell if your number is greater than 8 or something. Because if you're greater than 8, wait, what am I going to? Yeah, if you're greater than 8, you're going to land in this area here, which means you're 1 plus y. That would then be, then you multiply that by 2. And then you just add the x1. So the x would be add, it's an odd number, right? If you're an odd number, I think that gets you it. So if you're, yeah, I think that's right. We can double check it at some point. Yeah, odd number greater than 8. Yep. Okay, so now we've got that child index, does work. We should literally just be ORing over yeah, it should literally just be like making a bit set there, and that should be shareable across the waves. That's right. Good. So all it means we have to do now is set this guy. So we have to make sure that we transport. We need to actually atomically OR that in the LDS, and then pull it out. So we definitely need one of those weights, and then we need to share the. Well, no, we don't need to put it in the LDS. We just need to OR it into the buffer. So as long as we initialize this to 0, we should just be able to do a atomic bitwise OR 32 and just cram that in there, which is super nice. Now, storing it inside these, you need to kind of know which wave you're at. So you need to get like a wave index. The wave index is literally just cluster sphere index divided by 32. You'll truncate if you're 0 to 31 inclusively, and anything else should be 1. I'll get your wave index. So wave index, you'll set the sphere bit set. And then wave index again, you'll set the exclusive bit set. You still need to create the cluster node somehow. Mate, that children bits has already been done. So I don't know how we're going to set the... So we don't even have to wait here, which is really interesting. They can literally just do their stores and go. They might have to be atomic. Because if they're not atomic, then it means that other compute units are not going to be able to see their data. So how are we going to allocate the children here? So it's like, you probably need to put a barrier down. Yes, you probably put a barrier down. Yes, you probably put a barrier down, then allocate them all, and then initialize them all as well. Something like that. Right, so actually super close to doing the rewrite for the first shader. In the next stream, we're gonna finish this one off, and we'll update the rest of the shaders. But yeah, this is a good start. So just a bit of a warning: the next stream is on Tuesday. I'm actually going on holiday, like for the whole of February, so I won't be streaming the whole of February. I'll be back literally like the second week of March. But I should hopefully be here for Tuesday stream. But if I'm not, it's because I'm packing my suitcase. But should have it packed by then. It should be alright. But it might need to skip that one. Yeah, so we'll probably end up leaving this work like half, like kind of nearly finished, and we'll have to pick it back up after the month break. But yeah, it should be pretty awesome. Going on holiday, going to Australia. So I'm gonna be in the sun and outside. But yeah, I do have to jam right now because I have to get up for work tomorrow. So I'm just gonna find somebody to raid. But yeah, thank you for coming, everyone. There's a Discord if you guys want to come and chat and keep up to date on stuff, because I post in there things I'm thinking about and all that. You can also support the stream and get access to the code if you're a subscriber, or support via Ko-Fi. You can get access to the code there and run it on your local machine. That's cool, man. Yeah, these things happen. Or maybe I can keep going forever, and the sad time never appears. But yeah, just if only. Right, no one's on that. Let's see if there's anyone. Chill stream finishing our VM instructions. Clearly. Let's give the guy a raid anyway, since they're working on something cool. Or wait a minute. Right. Anyway, I'll post the VOD up on the channel. And yeah. Right. I'll catch you all in a future one. Thank you for coming. Have a good start to your work week, guys. Yeah. Awesome stuff today. Thank you so much. Right. Catch you later.